For generations, humanity believed our solar system was enormous, a huge space ruled by the sun and its planets. But now the James Webb Space Telescope has shown something surprising. Beyond Neptune's orbit, the universe is far bigger and more crowded than we ever imagined, filled with countless stars, galaxies, and worlds we can't even see. Compared to that, our solar system is actually very small. So how small is our solar system really? The James Webb Space Telescope is often described as humanity's great window into the universe, a vast and powerful instrument built not only to look at the stars, but to reach beyond what any human eye or telescope has ever seen before. It is a machine designed to reveal the hidden parts of the cosmos, those that have been invisible to us since the beginning of time. What makes this telescope truly special is not only its immense size or complex structure, but the way it brings together decades of human curiosity, engineering skill, and scientific ambition into one remarkable observatory that now floats far beyond the moon's orbit, silently watching the universe unfold. The idea behind the telescope's design began many decades before it was launched. Scientists and engineers wanted to create an observatory that could do more than just take pictures of stars. It had to look deeper into space, study light that had travelled for billions of years, and capture events that happened not long after the birth of the universe itself. To do this, they needed a telescope that could see infrared light, the kind of light that travels through dust and gas and reveals what ordinary telescopes cannot. The James Webb Space Telescope, or JWST, was designed around this very goal, to look farther back in time and deeper into the cosmos than any telescope ever built. At the heart of its design is a massive golden mirror. Unlike the small round mirrors found in older telescopes, this one looks like a shining honeycomb made of 18 hexagonal pieces. Each piece is coated with a thin layer of gold to reflect infrared light more efficiently. Together, these mirrors form a surface over 6.5 meters across, more than twice the size of the Hubble Space Telescope's mirror. To give a sense of scale, if Hubble's mirror were the size of a small car, then Webb's would be about the size of a house. The larger the mirror, the more light it can collect, and the farther it can see into the depths of space. However, building such a large mirror was not simple. A single solid mirror of that size would have been far too heavy to launch into space, and it would not fit into any rocket available. The solution came through innovation. The mirror was divided into 18 separate segments that could fold up for launch and then unfold like the petals of a flower once it reached space. Each segment can be adjusted independently, down to movements smaller than the width of a human hair, using tiny motors called actuators. This ability to fine-tune the mirror ensures that all segments work together perfectly as one, forming a single precise surface capable of focusing light with incredible accuracy. But the mirror alone could not make Webb the powerful observatory it is. Behind that shining golden surface lies a set of instruments so sensitive and advanced that they can detect the faintest glimmers of light from galaxies that formed over 13 billion years ago. These instruments are what truly turn Webb into a giant eye. There are 4 main scientific instruments, each with its own special job and unique way of seeing the universe. The first is called the Near-Infrared Camera, or NIRCam. It acts as Webb's main imager, capable of capturing incredibly sharp pictures in the near-infrared range. This camera allows scientists to study distant galaxies, newborn stars, and even planets orbiting other stars. NIRCam can detect objects so faint that they are invisible to most other telescopes, and it also helps in aligning the telescope's mirrors after launch. The second instrument is known as the Near-Infrared Spectrograph, or NIRSpec. Instead of just taking pictures, this device studies light in detail, breaking it apart into its different wavelengths like a rainbow. By analysing this light, astronomers can determine what elements and molecules are present in a star, planet, or galaxy. NIRSpec can observe more than 100 objects at once using tiny mechanical shutters, which is like taking the fingerprints of multiple galaxies in a single glance. The third instrument, the Mid-Infrared Instrument, MIRI, is what allows Webb to see even farther and deeper. It operates in the mid-infrared range, capturing light that has travelled from the earliest galaxies in the universe. MIRI is also capable of observing cooler objects, such as dust clouds where stars and planets are forming, as well as comets and asteroids in our own solar system. Because mid-infrared light is easily absorbed by heat, Miri must be kept extremely cold, at a temperature of about 7 degrees above absolute zero. To achieve this, Webb uses a special cryocooler system that chills the instrument far colder than any natural environment on Earth. The fourth and final instrument is the Fine Guidance Sensor, a near-infrared imager and slitless spectrograph, known as FGS-NIRIS. It helps the telescope maintain its incredibly precise pointing accuracy, while also carrying out important scientific observations. This instrument allows astronomers to study exoplanets, planets beyond our solar system, by analysing how their light changes as they pass in front of their stars. Together, these four instruments allow the telescope to perform an astonishing variety of tasks, from capturing images of the first galaxies that ever existed to studying the atmospheres of distant worlds that might harbour life. But for these instruments to work properly, they need protection from the sun's intense light and heat. That is where the telescope's enormous sunshield comes in. The sunshield is one of Webb's most striking features. It is as large as a tennis court and made up of 5 thin layers of a special material called kapton, coated with aluminum and silicon to reflect sunlight and heat. Each layer is thinner than a human hair, but together they can reduce the temperature between the hot and cold sides of the telescope by hundreds of degrees. On the side facing the sun, the temperature can reach nearly as hot as boiling water, while the shaded side, where the instruments are, stays colder than the most frigid Arctic night. Without this protection, Webb's sensitive instruments would be blinded by the heat and unable to detect faint infrared light. Because the telescope needs to stay so cold, it was placed far from Earth at a special location known as the Second Lagrange Point, or L2. This point lies about 1.5 million kilometers away, roughly 4 times farther than the Moon. At L2, the gravitational forces of the Earth and the Sun balance in such a way that the telescope can stay in line with both while orbiting the Sun. This stable environment allows Webb to keep its sunshield constantly facing the Sun and Earth, ensuring the instruments remain cold and undisturbed. The journey to reach this point was a delicate and risky one. After its launch in late December of the year 2021, aboard an Ariane 5 rocket from French Guiana, the telescope began a slow month-long journey to its final orbit. During this time, it had to unfold itself piece by piece, a process involving more than 300 separate steps, each of which had to work perfectly. Engineers on Earth watched closely as the massive sunshield spread out, the mirrors unfolded, and the instruments powered on. Any single failure could have ended the mission before it began, since the telescope was far too distant to be repaired by astronauts, unlike Hubble. When all deployments succeeded, the world breathed a collective sigh of relief. After decades of work and nearly $10 billion of investment, the telescope had come to life exactly as planned. The next few months were spent carefully aligning the mirrors and calibrating the instruments, until at last, in July of the year 2022, the first images were released. These images showed the universe in a way no one had ever seen before, filled with brilliant galaxies, glowing nebulae, and ancient light stretched by time itself. But what truly makes Webb capable of seeing farther and deeper than any observatory before it is the combination of its infrared sensitivity, massive mirror, and location beyond Earth's atmosphere. Telescopes on the ground, even the largest ones, must look through the air, which absorbs and distorts infrared light. Even Hubble, which orbits Earth, is limited because it mainly observes visible and ultraviolet light. Webb, on the other hand, is tuned to infrared, allowing it to peer through cosmic dust and detect the faint heat from the earlier stars and galaxies. When we look at distant galaxies with Webb, we're essentially looking back in time. Because light takes time to travel, the farther away an object is, the older the light we see from it. The telescope can detect light that has been travelling for more than 13.5 billion years, nearly to the dawn of the universe itself. Some of the galaxies it observes existed only a few 100 million years after the Big Bang, when the first stars were beginning to shine. In those earliest times, the universe was filled with dense clouds of hydrogen gas, blocking visible light. Only infrared light could pass through this fog. That is why Webb's infrared vision is so crucial. It can reveal those hidden moments when the universe was still young and dark, showing how the first stars ignited and how galaxies began to take shape. Webb's ability to capture such ancient light helps scientists answer some of the most profound questions. How did the first galaxies form? How did stars and planets begin? What are the conditions needed for life to emerge? These are not just scientific questions, but deeply human ones. touching on our own origins and our place in the cosmos. The telescope's design also includes technology to study planets outside our solar system in remarkable detail. Using its spectrographs, Webb can analyze the light from distant exoplanets as they pass in front of their stars. When starlight filters through a planet's atmosphere, it carries the fingerprints of the gases within it. By studying these fingerprints, scientists can identify whether a planet has water vapor, carbon dioxide, methane, or other chemicals associated with life. This ability opens an entirely new frontier in the search for habitable worlds. Before Webb, most exoplanet studies focused on detecting planets and measuring their sizes or orbits. Now, for the first time, astronomers can study what those worlds are actually like, their weather, composition, and perhaps even whether they could support life. Webb has already observed several known exoplanets and detected clear signs of water vapor and other atmospheric features, proving that its design exceeds expectations. Another fascinating part of Webb's mission involves studying the formation of stars and planetary systems. Inside giant clouds of gas and dust, new stars are born, but these regions are often hidden from view in visible light. Infrared light, however, passes through the dust, revealing what is happening inside. Webb can capture images of these star-forming nurseries in astonishing detail, showing how matter collapses under gravity to form stars, and how surrounding disks of gas and dust evolve into planets. Beyond our own galaxy, Webb observes the large-scale structure of the universe, the cosmic web of galaxies and dark matter that stretches across billions of light-years. By mapping these vast structures, astronomers can test theories about how gravity and dark energy have shaped the universe over time. The telescope's ability to see faint galaxies from the distant past helps piece together a timeline of cosmic evolution, showing how small clumps of matter grew into the massive galaxies we see today. To achieve all of this, Webb relies on precise engineering. Its mirror alignment system, for example, uses sensors and actuators that can move each segment by only a few nanometers, a scale so small that it would be like adjusting the height of a skyscraper by less than the width of a paper sheet. Its sunshield must remain perfectly stretched, and its orbit must stay stable to within a few kilometers, even while traveling at tens of thousands of kilometers per hour around the Sun. Communication with Earth is handled through NASA's Deep Space Network, which sends commands and receives data across vast distances. Every day, the telescope sends back terabytes of information, including high-resolution images and spectral data. Teams of scientists around the world then analyze this data, using it to make new discoveries and refine our understanding of the universe. Webb's mission goals extend far beyond its first few years. It was designed to operate for at least a decade, though its fuel supply could allow it to continue working for much longer. Over time, it will study everything from the icy moons of our solar system to the faint glow left over from the Big Bang. It may even help solve mysteries that we have not yet imagined. The success of the telescope's design was the result of international collaboration. NASA worked alongside the European Space Agency and the Canadian Space Agency, combining resources, expertise, and technology from across the world. Each partner contributed vital components. The European agency provided the launch and part of the spectrograph, while the Canadian agency built the fine guidance system. This teamwork reflects the shared human desire to explore the unknown and expand our understanding of existence. Every part of the telescope's structure was built with precision and purpose. The main body, or spacecraft bus, holds the electronics, communication systems, and propulsion units. It is what keeps the observatory powered, cooled, and pointed in the right direction. The telescope's instruments are mounted on an integrated science module, which connects directly to the mirrors. Together, these parts form a delicate balance of strength and lightness. The entire structure weighs only about 6.5 tons, remarkably little considering its enormous size and complexity. Keeping the telescope at the right temperature is one of its greatest challenges. The difference between the hot and cold sides of the sunshield is so extreme that it could cause thermal stress or distortions if not carefully managed. Engineers had to design materials that could survive such conditions for years without shrinking, stretching, or tearing. The layers of the sunshield are tensioned by a network of cables and pulleys, keeping them perfectly spaced so that heat cannot pass through. The observatory's pointing system is equally impressive. To capture sharp images of distant galaxies, Webb must remain steady to within a fraction of an arc second, roughly the width of a human hair seen from a kilometre away. This precision is achieved using reaction wheels, gyroscopes, and sensors that constantly adjust the telescope's orientation. This precision is achieved using reaction wheels, gyroscopes, and sensors that constantly adjust the telescope's orientation. Even the smallest vibrations must be controlled, and the fine guidance sensor ensures that the telescope locks onto its targets with unwavering stability. When people see the dazzling images Webb produces, it can be easy to forget the incredible amount of science and engineering behind each one. Every photograph represents countless calculations, alignments, and data corrections. The colours we see are not what the telescope sees directly, but are created by translating infrared light into visible colours so that human eyes can appreciate the hidden beauty of the cosmos. Each image tells a story of distant galaxies colliding, of stars being born, or of planets circling alien suns. The telescope's ability to see farther and deeper does not simply mean greater distance. It also means revealing more layers of the universe's history and structure. With each observation, Webb helps peel back another layer of mystery, whether it is the faint afterglow of the first galaxies or the chemical traces of life in another world's atmosphere. The instruments are designed to work together, creating a complete picture of what they observe. For instance, the near-infrared camera might detect a faint galaxy, while the near-infrared spectrograph studies its light to reveal its composition and motion. The mid-infrared instrument can then explore the same object to find cooler dust and gas, showing how stars are forming within it. This cooperation between instruments allows scientists to build a three-dimensional view of the universe across different wavelengths of light. The telescope's mirrors also contribute to this precision in a remarkable way. Each of the 18 segments is made of beryllium, a lightweight yet strong metal that performs well in extreme cold. After being polished and coated with gold, the segments were tested at cryogenic temperatures to ensure they would hold their shape. When assembled, they act as a single perfect mirror, reflecting light with extraordinary clarity. Because of these features, Webb can collect far more light than Hubble, making it over 100 times more powerful in certain observations. It can spot galaxies that are too faint for any other telescope, revealing how the universe transitioned from a dark, chaotic place into one filled with stars and galaxies. This period, known as the Cosmic Dawn, has long been one of astronomy's greatest mysteries, and Webb is finally providing the evidence needed to understand it. The telescope is not only looking outward in space, but also backward in time. It captures the story of how everything began, the slow formation of structure from the Big Bang, the creation of stars and the assembly of galaxies. Every speck of light in its images is a world, a collection of billions of suns, each with its own history. Even within our solar system, Webb has begun to transform our view. It can study the atmospheres of giant planets like Jupiter and Saturn, observe the icy moons of the outer planets, and detect faint objects in the distant Kuiper belt. Its infrared vision reveals details that no other observatory can see, such as heat signatures, chemical compositions, and changes over time. Through all these achievements, the telescope stands as a symbol of what human beings can accomplish when they work together with patience and imagination. It is the product of over 3 decades of planning, testing, and persistence. Thousands of people from many countries contributed to its creation, from the engineers who built its delicate mirrors to the scientists who designed its instruments and the teams who guide it across the void of space. The telescope's mission continues every day, sending back streams of data that help reshape our understanding of the cosmos. Each new observation adds another piece to the grand puzzle of existence. Whether it is revealing the first stars, uncovering new exoplanets, or studying the faint glow of ancient light, the James Webb Space Telescope remains our greatest tool for exploring the unknown, a giant eye in space, forever gazing into the past to illuminate the future. For thousands of years, human beings looked up at the heavens and believed that the universe revolved around them. The sun, the moon, and the bright points of light that appeared at night all seemed to move in perfect patterns across the sky, as though they were dancing around the Earth. This view, which came to be known as the geocentric model, dominated human thought for centuries. Ancient astronomers like Ptolemy built entire systems around this idea, believing that the Earth sat motionless at the centre of everything while crystal spheres carried the planets and stars around it. To early observers, the cosmos appeared enormous and majestic, yet in their minds, it all existed for humanity's sake. The idea of a vast universe beyond the planets was simply unimaginable. The stars were seen as distant decorations, lights attached to the edge of a heavenly dome. It was not arrogance as much as it was ignorance. Humanity simply did not have the tools to see farther or the means to question the illusion of size that the night sky presented. For the ancients, the visible sky was the limit of existence. The sun, the brightest and most dominant object in the sky, seemed vast and powerful, but even it was thought to be just one part of a universe designed around Earth. The distances between the planets appeared immense, but only because people had no real sense of measurement beyond what their eyes could see. The idea of distance in space was abstract, something guessed at but never understood. This illusion began to shift slowly during the Renaissance, a period of awakening that began in the 14th century and transformed the way people saw the world. In the early 16th century, a Polish mathematician named Nicholas Copernicus proposed something radical, that the sun, not the Earth, was at the centre of the universe. His model placed the Earth and the other planets in orbit around the sun, an idea that completely shattered centuries of belief. Yet even Copernicus underestimated the true scale of the solar system. He knew the planets were far apart, but he had no way of knowing just how far. To him and his followers, the sun still seemed close, the planets just beyond reach, and the stars still distant but part of the same grand structure. The idea that space could extend infinitely was almost too vast to accept. A few decades later, Galileo Galilei pointed a simple telescope at the sky and changed everything again. In the year 1610, he observed 4 small moons orbiting Jupiter, which proved that not everything revolved around Earth. He also saw that Venus went through phases just like the moon, showing that it must circle the sun. The illusion of a small Earth-centered universe began to crumble. Yet even as Galileo's discoveries opened new horizons, the solar system still appeared enormous to the human mind. It was the known edge of existence, a grand clockwork of celestial bodies moving in harmony, with the sun shining at its heart. Beyond the planets lay only mystery and speculation. Some thinkers believed the stars were other suns, perhaps even with their own planets, but there was no way to prove it. The solar system seemed vast, but it was still seen as the central masterpiece of creation. In the 17th century, Johannes Kepler calculated that planets moved not in perfect circles as once believed, but in ellipses. His laws of planetary motion allowed scientists to predict the movements of the planets with remarkable accuracy. Then Isaac Newton, in the late 17th century, explained gravity, the invisible force that held the planets in their orbits. These discoveries deepened humanity's understanding of the solar system's mechanics, but not yet its scale. The distances between the planets were measured in terms of astronomical units, the distance from Earth to the Sun, but even this was difficult to grasp. The numbers were so large that they meant little to ordinary people. To most, the solar system remained an unfathomable expanse, an enormous cosmic sea that humanity could never cross. By the 18th and 19th centuries, astronomers had discovered Uranus and Neptune, expanding the boundaries of the known solar system. William Herschel, who discovered Uranus in 1781, believed he had reached the edge of creation itself. The planets seemed to stretch endlessly outward from the Sun, forming a vast family of worlds. The idea of the solar system as the ultimate frontier became deeply rooted in the imagination. Artists, poets, and scientists alike described it as an enormous celestial empire ruled by the Sun, with each planet a kingdom of its own. To think that there might be more beyond was almost heretical. Humanity was still trapped in a comforting illusion, the belief that their cosmic neighbourhood was the entire universe. Even the discovery of comets and asteroids did little to change this perception. When telescopes became more powerful in the 19th century, they revealed countless smaller bodies orbiting between Mars and Jupiter, forming what came to be known as the asteroid belt. To many, it seemed that the solar system was filled with endless objects, stretching farther than anyone could imagine. The distances between planets were described in millions and billions of miles, but such numbers were so large that they lost all meaning. To the human mind, the solar system was a vast, almost infinite realm, the ultimate measure of cosmic scale. People imagined the edge of the solar system as a dark, frozen boundary where the sun's light faded into the void beyond which nothing existed. Then, in the early 20th century, the illusion began to weaken once more. Telescopes grew stronger and astronomers started to suspect that the stars were not just part of our solar system, but distant suns, each with its own possible worlds. In the 1920s, Edwin Hubble made a discovery that forever shattered humanity's understanding of size. Using the 100-inch Hooker telescope at Mount Wilson Observatory, he found that the Andromeda Nebula was not a cloud of gas within our galaxy, as once thought, but a completely separate galaxy, one of countless others. This revelation transformed the solar system from being the centre of creation to being merely one small corner of an unimaginably vast universe. The illusion of size that had lasted for millennia was finally broken, yet many still found comfort in the familiar grandeur of the solar system. Even so, the sense of distance within our own cosmic neighbourhood continued to inspire awe. The Sun was nearly 150 million kilometres from Earth, a figure that seemed unthinkably large. The outer planets were so far away that even light, travelling at nearly 300,000 kilometres per second, took hours to reach them. When astronomers spoke of these numbers, they felt almost poetic. The solar system still appeared enormous compared to human experience, but now it was understood to be only a tiny part of something far greater. The mid-20th century brought another turning point. For the first time, humanity began to send machines beyond Earth's atmosphere. In the year 1957, the Soviet Union launched Sputnik, the first artificial satellite, and only a few years later, Yuri Gagarin became the first human to orbit Earth. These milestones marked the beginning of space exploration, and soon after, humanity turned its gaze outward, toward the moon, the planets, and the far reaches of the solar system. The illusion of size began to transform once again, this time through direct exploration rather than theory. In the 1960s and 70s, robotic probes ventured to the nearby planets. The Mariner missions sent back the first close-up images of Venus and Mars, revealing worlds that were not distant mysteries but solid places, barren, rocky, and real. When the Apollo missions landed humans on the Moon in 1969, the solar system suddenly felt smaller. For the first time, people saw Earth from space, a fragile blue sphere floating in darkness. The vastness that had once seemed endless was now something humanity could measure and explore. Yet even as the solar system grew more familiar, it still felt huge. The outer planets, Jupiter, Saturn, Uranus, and Neptune, remained far beyond the reach of human travel, and the Sun's outer domain was still wrapped in mystery. The illusion of the solar system's size reached its greatest test in the late 20th century with the launch of the Voyager probes. In the year 1977, NASA sent two spacecraft, Voyager 1 and Voyager 2, on grand journeys to explore the outer planets. These missions changed human understanding of space forever. Over the years, the Voyagers sent back breathtaking images of Jupiter's swirling storms, Saturn's shimmering rings, Uranus's tilted atmosphere, and Neptune's deep blue winds. Each planet, once thought to be just points of light, was revealed in stunning detail. The solar system no longer seemed like an abstract diagram in a textbook. It became a living, dynamic place. As the Voyagers continued their journeys beyond Neptune, they entered a region known as the Kuiper Belt, a vast field of icy bodies and dwarf planets. Beyond that lay the mysterious Oort cloud, a hypothetical shell of comets stretching nearly 2 light-years from the Sun. Even at these extreme distances, the Sun's gravity still held sway. Voyager 1 eventually crossed the boundary known as the heliopause in the year 2012, entering interstellar space. For the first time, a human-made object had left the solar system. Yet, in the grand scale of the cosmos, it had barely moved at all. The probe, travelling at nearly 60,000 kilometers per hour, would take tens of thousands of years just to reach the nearest star. What once seemed enormous, the solar system, was now just a tiny bubble in an endless ocean of space. This realization was both humbling and astonishing. For most of human history, the solar system had represented the ultimate boundary of existence. Early astronomers had gazed upward and believed they were looking at the whole of creation. Even as telescopes revealed more detail, the scale of the solar system still seemed vast beyond comprehension. But as science advanced, and as spacecraft like Voyager ventured farther and farther away, the truth became undeniable. The solar system was not the universe's centre, nor even a large part of it. It was merely a small family of planets orbiting an ordinary star among billions of others. The illusion of size had been built not on arrogance but on perspective. Human senses are limited to what the eyes can see and the mind can imagine. When people first measured distance by walking across the land or sailing across the sea, even the moon seemed impossibly far away. The early astronomers could not have imagined distances measured in millions or billions of kilometres. To them, the heavens were vast because their world was small. As tools improved, from simple telescopes to giant observatories and finally to space probes, that perspective widened, and what once seemed enormous began to shrink. The transformation of this perception can be traced through humanity's changing relationship with scale. In the 17th century, a telescope that magnified the moon made people feel as though they had touched another world. In the 20th century, photographs taken by robotic explorers made the outer planets seem almost close. In the 21st century, space observatories like the Hubble and the James Webb Space Telescope have peered beyond the solar system entirely, capturing light from galaxies that formed billions of years ago. Each step has revealed that our solar system, while wondrous and complex, is a mere speck in a cosmic web that stretches across unimaginable distances. Still, for the people of earlier times, the illusion of size was powerful. It shaped myths, religions, and philosophies. The planets were gods, the stars were eternal fires, and the sun was the life-giving heart of the universe. The solar system was not only vast, it was sacred. To suggest otherwise was to challenge the very order of creation. When Copernicus, Galileo, and Kepler presented their findings, they were not only changing science, they were reshaping humanity's place in the cosmos. The solar system became a stage for discovery rather than divine perfection, but its immensity remained awe-inspiring. Even as humanity's knowledge grew, the feeling of vastness never fully faded. The distances within the solar system are still immense compared to human experience. It takes light more than 8 minutes to travel from the Sun to Earth. It takes over 5 hours to reach Pluto, the small icy world that marks the outer edge of the main planetary system. A spacecraft travelling at tens of thousands of kilometers per hour takes years just to move between neighbouring planets. The illusion of size may have been replaced by understanding, but the sense of wonder remains. The Voyager probes, now drifting through the interstellar medium, continue to send faint signals back to Earth, whispers from the edge of the Sun's influence. They remind humanity of how far it has come and how small it still is. The once vast solar system is now just a pinpoint of light within the Milky Way galaxy, which itself is one among hundreds of billions of galaxies in the observable universe. Yet for early astronomers who had no concept of galaxies or cosmic scale, the solar system's grandeur was enough to fill the imagination. This long journey, from the early star watchers of ancient Babylon to the deep space travelers of the modern era, reveals more than scientific progress. It shows the evolution of human humility. Each discovery that made the universe larger also made humanity smaller. Once, people thought the Earth was the centre of all things. Then they learned that it was only one planet among many. Later, they discovered that the Sun was just one star among countless others. Finally, they began to see that even the galaxy itself was not unique. The illusion of size was not destroyed in a single moment, but peeled away layer by layer, replaced by a deeper understanding of reality. And yet, the illusion still has power. When people look at images of Saturn's rings or Jupiter's storms, the mind struggles to grasp their true scale. Saturn's rings stretch hundreds of thousands of kilometers wide, but they are so thin that they would fit easily between clouds on Earth. Jupiter's great red spot, a storm larger than our entire planet, rages continuously as though it were eternal. These facts are both real and surreal, showing that even within the solar system's relatively small scale in cosmic terms, there is still an immensity beyond ordinary imagination. From the first moment an ancient observer marked the motion of Venus to the time when Voyager 1 crossed into interstellar space, the human sense of scale has expanded 1,000-fold. What was once seen as the universe is now known to be a small neighbourhood of cosmic space. But in that smallness lies a profound truth, that humanity's ability to perceive and explore has grown far beyond its physical limits. The illusion of size may have been an error, but it was also a necessary step in the path of understanding. Without it, there might have been no reason to reach beyond the stars, no desire to discover what lies beyond. The story of how humanity once believed the solar system to be vast and central is also the story of how curiosity overcame illusion. Every telescope built, every calculation made, and every probe launched has brought the universe into sharper focus, revealing both its enormity and our own smallness within it. The early astronomers, limited by what they could see, created a cosmos centered around humanity. The explorers of later centuries replaced that illusion with knowledge, a knowledge that continues to grow as new generations push further into the unknown. Even now, as telescopes peer into galaxies billions of light-years away, the solar system retains its sense of wonder. It remains the cradle of life, the place where consciousness first opened its eyes to the stars. It may no longer seem enormous in comparison to the vastness of the universe, but to humanity, it will always be the first great ocean crossed by the ships of discovery. The illusion of size that once made the solar system seem infinite has faded, replaced by a more profound realization that the true vastness of the universe lies not just in distance, but in the endless reach of human curiosity. It began with a single image, one that would forever change how humankind sees the universe. The James Webb Space Telescope, after years of careful planning, construction, and anticipation, released what became known as its first deep field, a view so astonishing that even the scientists who had worked on the mission for decades were left speechless. The image revealed thousands upon thousands of galaxies crowded into a space so tiny that, if you held up a grain of sand at arm's length, the patch of sky it covered would be even smaller. Yet within that tiny window, the telescope captured an almost endless ocean of galaxies, each one containing billions of stars, countless planets, and perhaps unknown forms of life. It was not simply a photograph, it was a glimpse into infinity itself. For centuries, people believed the universe was vast but still somewhat limited, a grand stage with stars scattered like lights across a dark ceiling. Even the best telescopes of earlier times could only reveal so much: a few distant galaxies, faint smudges of light, some nebulae, and the countless stars of our own Milky Way. When the Hubble Space Telescope took its famous deep-field image in the late 1990s, astronomers were stunned to discover thousands of galaxies in what seemed like an empty patch of space. That image alone changed the way humanity understood its place in the cosmos. But the James Webb Space Telescope went even deeper, peering farther into the past than anyone thought possible, reaching back to a time when the first galaxies were just beginning to form, only a few 100 million years after the Big Bang, the very dawn of cosmic history. The light from those galaxies had travelled for more than 13 billion years to reach Webb's golden mirrors. In other words, the telescope was not just looking across space, but back through time itself. The faint glimmers it recorded were ancient messages from a universe still young, a universe where the first stars were igniting, shaping the elements that would one day make planets, oceans, and life. What Webb saw was not the present-day cosmos, but the universe as it once was, fragile, chaotic, and newborn. The image itself, known officially as SMACS 0723, is one of the most extraordinary pictures ever captured. It shows a massive cluster of galaxies in the foreground, located billions of light-years away. These galaxies are so heavy that their combined gravity bends and magnifies the light coming from even more distant galaxies behind them, creating a natural effect known as gravitational lensing. This phenomenon acts like a giant cosmic magnifying glass, allowing the telescope to see even farther into the universe than it otherwise could. Some of the distorted arcs and streaks of light in the image are actually entire galaxies whose light has been stretched and warped by the immense gravitational pull of the cluster. What we see, then, is a cosmic tapestry woven from light that has journeyed across most of the universe's lifetime. When the image was first shown to the world in July of the year 2022, the reaction was one of collective awe. People who had never cared much about astronomy before found themselves staring in silence, overwhelmed by the realization of just how small our world truly is. The image was rich in color, deep reds, soft blues, and glowing whites, each hue representing light from galaxies at different distances and ages. The deeper the red, the older and farther away the galaxy. Those red dots and stretched shapes were not stars at all, but vast galaxies, each containing millions or even billions of suns. In that single frame, Webb revealed that the universe is far more crowded, far more complex, and far more ancient than any previous telescope had shown. To capture that image, the James Webb Space Telescope had to perform with extraordinary precision. It orbits the Sun roughly 1.5 million kilometers away from Earth, at a place known as the second Lagrange point, where the gravitational forces of Earth and the Sun balance just right to keep it stable. From that quiet location, Webb unfolds its massive gold-coated mirror, made up of 18 hexagonal segments, and its sun shield, as large as a tennis court, which protects its instruments from heat and light. Webb's cameras and spectrometers operate at extremely cold temperatures, allowing them to detect faint infrared light, the kind of light that comes from the most distant objects, whose wavelengths have been stretched over billions of years as the universe expands. The deep field image was created using data from one of Webb's main instruments, the Near-Infrared Camera, or NIRCam. This instrument can detect light invisible to the human eye, allowing astronomers to see the ancient red-shifted glow of galaxies formed not long after the Big Bang. To make the image, the telescope observed its chosen patch of sky for more than 12 hours, collecting light that had been travelling for over 13 billion years. The result was a portrait of the universe as it looked when it was still young, less than 1 billion years old. Every single point of light in that picture represents not a star but an entire galaxy, each one home to billions of stars and each of those stars possibly surrounded by planets. When scientists realized how many galaxies were visible in such a tiny region, they began to imagine how many must fill the entire sky. If a speck smaller than a grain of sand contains thousands of galaxies, then the total number across the universe could be beyond human comprehension, perhaps hundreds of billions, maybe even more. And if each of those galaxies holds countless stars, then the number of planets may be so vast that it defies imagination. What Webb revealed in that moment was the true scale of existence. Our Milky Way, enormous as it seems, is only one small swirl among countless others. The Sun, which dominates our sky, is merely one of about 200 billion stars in our galaxy, and yet it is insignificant compared to the number of stars scattered across all the galaxies in the image. The Earth itself, our home, becomes almost invisible, a tiny pebble orbiting an ordinary star in an ordinary galaxy, lost among an unimaginable sea of others. The deep field reminded humanity that our place in the cosmos is incredibly small, but it also showed how lucky we are to exist at all, capable of observing and understanding even a fraction of this infinite beauty. Scientists spent months studying the image in detail. Hidden within it were clues about the earliest stages of cosmic evolution, the birth of the first stars, the formation of the first galaxies, and the mysterious dark matter that shapes their structures. Many of the galaxies in the image appear stretched or distorted because of gravitational lensing, but that distortion actually helps researchers measure distances and infer the amount of dark matter present in the cluster. Others appear unusually red, suggesting they are among the most distant and oldest ever observed. By analysing the light from these ancient galaxies, astronomers can learn about the chemical elements they contain, revealing when the first heavy elements like carbon, oxygen, and iron began to form, the same elements that make up stars, planets, and life itself. Before Webb, such ancient galaxies were beyond the reach of human observation. The Hubble Space Telescope could only detect them faintly or not at all, because their light had been stretched too far into the infrared range. Webb's infrared vision, however, allowed scientists to peer across cosmic time and see the universe as it was less than 1 billion years after its beginning. In a sense, it allowed humanity to witness the first dawn, the earliest flicker of light after the long cosmic night that followed the Big Bang. What makes the image even more profound is the idea that this is only the beginning. The field of view is incredibly small, yet it contains thousands of galaxies. That means that if Webb were to take similar images across different parts of the sky, it could reveal millions more. Each one would hold stories of its own: collisions, mergers, starbursts, and the quiet deaths of ancient suns. The light from those galaxies carries with it the history of everything that has ever been. To study that light is to study time itself. In the months following the release of Webb's first deep field, astronomers began comparing it with other deep fields taken by Hubble, and the difference was astonishing. Where Hubble saw faint smudges, Webb saw detailed structures, spiral arms, glowing gas clouds, and clusters of newborn stars. Some of the galaxies Webb detected are so distant that they appear as they were less than 500 million years after the Big Bang, when the universe was still filled with a thick fog of hydrogen gas. These galaxies helped reionize that gas, clearing the cosmic fog and allowing light to travel freely through space. By studying them, scientists hope to understand how the first stars and galaxies transformed the universe from darkness into light. The image also offers a humbling sense of scale. The foreground cluster itself, SMACS 0723, is located about 4.5 billion light-years away, meaning its light began travelling toward us before the Earth even existed in its current form. Behind that cluster, Webb captured light from galaxies even farther away, some whose light began its journey more than 13 billion years ago. The mind struggles to grasp what those numbers mean. A single light-year is the distance light travels in 1 year, about 9.5 trillion kilometres. Multiply that by billions, and the scale becomes beyond human comprehension. Yet Webb's instruments made it possible to record and analyse that light with exquisite precision, turning what was once invisible into something we can see and study. Every speck of that image tells a story written in light. Some galaxies are young and blue, full of new stars burning hot and fast. Others are old and red, their stars aging and dying. Some show signs of collisions, where two galaxies have merged to form one larger system. Others exist in isolation, quietly drifting through space. There are galaxies shaped like spirals, ellipses, and irregular clouds, each with its own structure and history. And yet, despite their variety, they all obey the same cosmic laws, following the same physics that governs our own world. When you look closely at the image, you can see faint arcs of light stretching around the centre of the cluster. Those arcs are not tricks of the camera. They are real distortions caused by gravity. The cluster's mass bends space-time itself, just as Einstein predicted in his theory of general relativity more than a century ago. The light from more distant galaxies travels through this warped space, curving as it moves, creating the strange shapes we see. By measuring how much the light is bent, scientists can estimate the amount of mass, including invisible dark matter, present in the cluster. In this way, Webb's deep field is not just a picture, it is a scientific map, a window into the invisible forces shaping the universe. The deep field image also holds emotional power. For many people, it evokes a feeling of wonder and humility. To realize that every tiny point of light represents a galaxy filled with stars and planets is to confront the true vastness of creation. It challenges human ideas of importance, reminding us that our world is only one small part of an endless cosmos. Yet it also connects us to something greater, a shared universe that we are part of, and which we can now see with our own eyes thanks to human curiosity and ingenuity. The technology that made this possible is itself a triumph of human achievement. The James Webb Space Telescope took decades to design and build. Thousands of scientists, engineers, and technicians from many countries worked together to create a machine capable of unfolding itself in space with flawless precision. Every mirror segment was polished to nanometer accuracy. Every instrument was tested for years, and every step of its deployment was rehearsed countless times. The telescope had to travel 1.5 million kilometers from Earth, unfold its mirrors and sunshield perfectly, and cool down to temperatures near absolute zero before it could begin its work. The success of that process was a testament to both science and cooperation, proof that humanity can reach for the impossible and achieve it. When Webb's first deep field was released, it did more than show us galaxies. It showed us the power of curiosity. It reminded us that no matter how far we've come, there is always more to discover. Each tiny dot in that picture represents a mystery, how that galaxy formed, how its stars live and die, what kinds of planets might orbit those stars, and whether life could exist there. Some of the galaxies are so far away that their light has been stretched to such long wavelengths that it borders on the limits of detection. Yet even that faint light carries secrets about the earliest times in the universe, about how matter gathered, stars ignited, and galaxies took shape. The image also serves as a bridge between the past and the future of astronomy. Hubble gave us our first deep look into the cosmos. Webb extends that vision even farther, but the story does not end here. In the years to come, Webb will continue to take more deep field images, exploring different regions of the sky, revealing galaxies even older and fainter. It will study the atmospheres of exoplanets, search for the chemical fingerprints of life, and investigate the birth of stars within dusty clouds. Each discovery will add to the tapestry of knowledge that began with that first image, that first glimpse into infinity. There is something profoundly poetic in the fact that the image of countless galaxies comes from such a small piece of sky. It teaches a quiet lesson about perspective, that greatness can be hidden in the smallest things, and that what seems empty may, in truth, be overflowing with life and meaning. The patch of sky Webb observed was chosen precisely because it appeared empty to the naked eye, a region with few stars or nearby objects to interfere. Yet within that apparent void lay the story of the entire universe. In that way, the deep field reminds us that there is no true emptiness in the cosmos, only distances too vast for our eyes to see until now. The scientists who analysed the data found that some of the galaxies in the image are among the most distant ever discovered. Their light began its journey less than 500 million years after the Big Bang, when the universe was only about 4% of its current age. These galaxies are extremely faint and small, but Webb's sensitivity allowed astronomers to detect their light clearly. By studying them, scientists hope to understand how the earliest galaxies formed and evolved, how they gathered stars and gas, and how they eventually grew into the massive galaxies we see today. Webb's deep field also offers a tool for understanding dark energy, the mysterious force causing the universe's expansion to accelerate. By mapping the distances and shapes of galaxies across time, astronomers can trace how cosmic expansion has changed, offering clues about the nature of this invisible energy. Every deep field image, then, becomes a piece of a larger puzzle, one that may eventually reveal the ultimate fate of the universe. For now, however, what the image gives most clearly is wonder, a sense of awe that words can barely capture. The light in that photograph began its journey billions of years before the Earth existed, long before the Sun was born. For eons it travelled through the void, passing stars, galaxies, and clouds of interstellar dust, until it finally reached the golden mirrors of the James Webb Space Telescope. There, in a moment of perfect alignment, the light was captured, recorded, and turned into an image that we could see, a story that began before humanity and will continue long after us. It is humbling to realize that this light, which left its source before our planet even formed, now allows us to look back to the beginning of everything we know. The galaxies in that image are ancient beyond comprehension, yet their light shines across time to reach our modern instruments. That connection between past and present, between the birth of the universe and the curiosity of human beings, is what gives the image its power. It is a reminder that we are part of a much larger story, one that stretches across billions of years and countless stars. The James Webb Space Telescope's first deep field is not only a scientific triumph, but also a moment of shared human reflection. It shows that despite our smallness, we are capable of great understanding. It reveals that the universe is not a cold, empty void, but a place overflowing with structure, beauty, and history. And in that realization lies something profoundly moving. The sense that, though we are small, we are connected to everything. Each of us is made from the same stardust that once burned in those ancient galaxies, and now, after billions of years, we have built a tool capable of seeing where it all began. The James Webb Space Telescope has forever changed the way humanity sees its place in the universe. For thousands of years, people looked up at the sky and believed the sun, moon, and planets were the most impressive things that existed. The solar system seemed so enormous that it felt like the entire universe must revolve around it. The distance from Earth to the sun alone was thought to be almost beyond imagination, and the great planets, Jupiter, Saturn, Uranus, and Neptune, appeared to float at unreachable distances. But now, with the incredible power of the James Webb Space Telescope, that sense of scale has been shattered. What once felt infinite now appears small, fragile, and almost invisible when compared to the vast ocean of galaxies beyond. The Webb telescope has shown humanity that our solar system, which contains the sun and all its planets, moons, comets, and asteroids, is only one tiny speck in a universe filled with countless other systems. Every single point of light in Webb's deep space images that looks like a star is, in most cases, a galaxy, an entire collection of billions of stars, planets, and possibly even life. This realization has completely transformed our understanding of size, distance, and importance. The same sky that ancient people once believed held the limits of creation is now known to be just a microscopic piece of something so huge that even our most powerful minds struggle to grasp it. To appreciate what Webb revealed, one must imagine what it means to find thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Each of those galaxies may contain hundreds of billions of stars, and many of those stars could have their own planetary systems. That means that in just one minuscule corner of the sky, there might be trillions of worlds, some perhaps like ours, and others completely unlike anything we can imagine. Webb's view has shown that the scale of existence extends far beyond the Sun and its 8 known planets. Our solar system, which once felt like an endless realm, is merely a drop in an endless cosmic ocean. The contrast between what humanity once believed and what Webb has revealed is stunning. In the early centuries of human civilization, astronomers like Ptolemy imagined the Earth to be at the center of everything. The stars were thought to be tiny lights fixed on a crystal sphere surrounding the planet. Later, when Copernicus, Galileo and Kepler showed that Earth was not the center, but rather one planet circling the Sun, it was a huge revolution. The solar system became the new center of importance. Then, in later centuries, as telescopes improved, scientists realized that the Sun itself was just one star among many in the Milky Way galaxy. That discovery alone was humbling, but even then the Milky Way was thought to be the whole universe. It was not until the 20th century that astronomers like Edwin Hubble discovered that there are other galaxies beyond our own. That discovery expanded our known universe from one galaxy to billions. Yet even with those earlier telescopes there were limits. The faintest, most distant galaxies could only be seen as blurry smudges of light. What Webb has done is to remove that blur and show, in stunning clarity, just how many galaxies are out there, and how incredibly far away they are. The distances involved are so vast that light from some of these galaxies has travelled for over 13 billion years to reach us. That means we're not only seeing faraway places but also looking back in time, witnessing the universe as it was soon after its birth. This shift in perspective makes the solar system appear unimaginably small. Consider that the entire span of our solar system, including the outermost reaches where the icy bodies of the Oort cloud drift, stretches about 1 light-year from the Sun. That might sound immense, but it is almost nothing compared to the distances between stars and galaxies. The nearest star system to our own, called Alpha Centauri, is more than 4 light-years away. The Milky Way galaxy itself is 100,000 light-years across, and it contains hundreds of billions of stars. And the observable universe, which is only the portion we can see, stretches across more than 90 billion light-years. When Webb captures a deep field image, it is looking so far into space that the light it records has been travelling for nearly the entire age of the universe. Each galaxy in those images represents not just a distant object, but a different era of cosmic history. Some galaxies are fully formed and filled with mature stars, while others are young and still glowing with the energy of their firstborn suns. Within each one could exist countless solar systems, each with its own arrangement of planets, moons, and possibly even living creatures wondering about their place in the cosmos. The realization that billions of galaxies exist, and that each galaxy may have billions of stars, has made the solar system feel both precious and insignificant. The planets that once seemed far apart now appear close together, huddled around a modest star on the edge of one galaxy among countless others. Webb's view of the universe forces humanity to confront how small it truly is. Yet paradoxically, this also makes our existence more remarkable. The odds of life arising in such a vast universe might seem incredibly small, but if there are countless planets scattered across billions of galaxies, then perhaps life is not so rare after all. The Webb telescope's design allows it to observe in infrared light, which means it can see objects that are invisible to human eyes. This ability to detect faint ancient light allows scientists to peer beyond the reach of older telescopes like Hubble. Where Hubble could only see certain wavelengths, Webb's mirrors and sensors are tuned to capture the glow of the earliest galaxies, whose light has been stretched and dimmed by billions of years of cosmic expansion. This makes Webb not just a telescope but a time machine that lets us witness the early universe. In Webb's deep field images, each pinpoint of light carries a story billions of years old. The galaxies it reveals come in all shapes and sizes: spirals, ellipticals, and irregular clusters that seem to defy symmetry. Some are vast, containing trillions of stars, while others are tiny and dim, made up of only a few million suns. Together they fill the frame of Webb's vision, leaving no space untouched by the presence of light and matter. The sheer density of galaxies in those pictures is enough to overwhelm the human mind. It makes the solar system, even the entire Milky Way, seem like a single grain of sand in an endless desert. Before Webb, humanity's understanding of the universe's structure was already immense, but its details were hidden. Now, with Webb's clarity, scientists can trace how galaxies formed and evolved over time. They can see the birthplaces of stars within cosmic clouds, the merging of galaxies that create massive new systems, and the faint glows of galaxies from an era when the universe was still young. This knowledge reshapes everything we thought we knew about scale. It reveals that our solar system, though intricate and beautiful, is a single flicker in a vast network of cosmic creation. To grasp just how small we are, consider this. If the Milky Way were reduced to the size of the entire continent of Africa, our solar system would be smaller than a single grain of sand on one of its beaches. The Sun, which dominates our skies and gives life to Earth, would be nothing more than a speck too small to see. The planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, would be invisible dots circling that speck. Even so, every person who has ever lived has existed within that microscopic space. Every story, every civilization, every dream has unfolded on that tiny grain within the grandness of the cosmos. When Webb observes the distant universe, it sees galaxies that existed when the universe was only a few 100 million years old. The light from those galaxies has travelled for more than 13 billion years to reach us. In that time, countless stars have been born and died, planets have formed and disappeared, and entire galaxies have collided and merged. Meanwhile, our own solar system only formed about 4.5 billion years ago, long after many of those ancient galaxies had already begun to evolve. This means that by the time Earth was born, much of the universe was already filled with galaxies older than our Sun. The knowledge of this timeline changes how humanity perceives itself. For so long, people believed the Sun was ancient and enduring, yet in cosmic terms, it is relatively young. Webb's deep space observations reveal galaxies that existed when the universe was less than 10% of its current age. Those galaxies are filled with stars far older than our solar system. The light they emit is a message from a time before Earth even existed, a faint echo of the universe's earliest moments. To think that our small solar system is just one among countless others in such an immense and ancient cosmos is both humbling and awe-inspiring. Every discovery Webb makes adds another layer to this cosmic perspective. The telescope has shown galaxies so faint and distant that their light barely reaches us, and yet even these faint glimmers represent massive structures containing billions of suns. The space between galaxies, once thought to be empty, is filled with faint radiation, drifting gas, and mysterious dark matter that holds the universe together. On such scales, even the vast orbits of our outermost planets are insignificant. Neptune, which seems so distant from Earth, lies only a few billion kilometers away, nothing compared to the trillions upon trillions of kilometers between galaxies. The distances Webb measures defy comprehension. Light travels at about 300,000 kilometers per second, yet it still takes light from some galaxies more than 13 billion years to reach us. If a beam of light left one of those galaxies when the universe was young, it would have travelled across space for the entire history of stars, planets, and life before arriving at Webb's sensors. The telescope captures that ancient glow, converting it into images that let us see the universe as it was long before humans existed. In doing so, it places our small solar system within an unimaginable timeline that stretches from the dawn of creation to the present day. Even though the solar system is vast by human standards, it becomes almost meaningless when compared to these cosmic scales. The distance from the Sun to Neptune is about 4.5 billion kilometers, and beyond that lies the Kuiper Belt and the Oort cloud, a distant region filled with icy fragments. Yet, all of this, the entire realm governed by the Sun's gravity, is only a microscopic bubble in the immensity of space. Beyond it lies the interstellar void, and beyond that, billions of other star systems, each surrounded by their own planets and debris. Webb's observations have made it impossible to view the solar system as anything other than a single spark in a universe overflowing with light. This awareness can be overwhelming. the sheer number of galaxies revealed by Webb challenges the imagination. Scientists estimate that there may be more than 2 trillion galaxies in the observable universe. If each galaxy holds 100 billion stars, that means there are more stars in the cosmos than there are grains of sand on all the beaches of Earth. Each of those stars could have planets orbiting it. Some of those planets could be small and rocky like Earth, orbiting at just the right distance from their star for liquid water to exist. The possibility that there might be countless other Earth-like worlds hidden within those galaxies gives new meaning to the question of whether we're alone. The Webb telescope's deep-field views show the structure of the universe as a vast web of galaxies connected by invisible threads of gravity and dark matter. Between those threads are enormous voids, each spanning hundreds of millions of light-years. These cosmic structures give shape to the universe, showing how matter gathered over billions of years to form stars, clusters, and galaxies. When viewed on such scales, the solar system disappears completely. Even the Milky Way itself becomes a single point within a massive cosmic tapestry. Webb has revealed that the universe is not only large, it is layered with complexity beyond anything humanity has ever known. And yet, within this vastness, there is something profoundly meaningful about the tiny solar system. It may be small, but it is also the only place we know where life exists. All the beauty and consciousness that humanity has ever known come from that minuscule region of space. The same light that Webb captures from distant galaxies also shines on Earth, nourishing its oceans, forests, and living beings. The realization that such life arose in a corner of a universe filled with billions of galaxies gives the solar system a kind of quiet importance. It is small, yes, but it contains the awareness to look outward and understand the enormity of what lies beyond. Webb's discoveries have not only expanded scientific knowledge, they have altered human imagination. No longer can anyone look at the stars and think of the universe as a simple, orderly place centered on the sun. Now we know that we are part of something almost beyond comprehension. The solar system is just one among endless systems, orbiting one star among countless others, in one galaxy among billions. Every time Webb takes another deep look into space, it reminds us how astonishingly vast the cosmos is, and how extraordinary it is that we are able to witness even a tiny piece of it. Through Webb's lens, distances are stretched to their limits, and time itself becomes visible. Light that began its journey billions of years ago now meets our eyes, carrying the story of a universe that has been growing and changing for nearly 14 billion years. Each galaxy Webb reveals is a chapter in that story, a reminder that everything we see today has roots deep in cosmic history. The solar system, formed from the debris of earlier generations of stars, is a product of that long chain of creation. Every atom in our bodies was forged in the heart of ancient stars that once shone in galaxies far older than our own. So when Webb shows us a field filled with countless galaxies, it is not just showing distant places, it is showing our origins. The matter that makes up Earth, the Sun, and all living beings was once part of that distant universe. The hydrogen in our oceans, the carbon in our bodies, the iron in our blood, all of it was created long ago in stars that lived and died in galaxies scattered across space. Webb's deep images remind us that we are not separate from the universe, but made of the same elements that shine in those faraway galaxies. The contrast between the solar system's smallness and the universe's vastness does not make humanity insignificant. It connects us to everything. Every discovery Webb makes ties us to a greater whole, revealing the beauty and complexity of a cosmos where scale defies understanding. The telescope's observations continue to push the boundaries of knowledge, uncovering new galaxies, new stars, and perhaps one day, signs of other worlds like our own. Each new image deepens the sense of wonder, showing that even though our solar system is tiny, it is part of an infinite story that stretches across time and space. In the late 20th century, a small spacecraft was drifting quietly through the outer edge of the solar system. It had already completed its main mission, visiting the giant planets, Jupiter and Saturn, and sending home breathtaking pictures that transformed how humanity saw its own neighborhood in space. As it moved farther away from the Sun, engineers decided to turn its cameras one last time toward home. What it captured would become one of the most humbling images in all of human history. From billions of kilometers away, the camera saw Earth as nothing more than a faint speck, a single pale blue dot suspended in a vast ocean of darkness. That image, taken by the Voyager spacecraft in the year 1990, changed forever how people understood their place in the universe. The picture was not impressive by modern standards. There were no dazzling galaxies, no vivid clouds of cosmic gas glowing in colour, no grand planetary details. Just a few shafts of sunlight scattered across the camera lens, and within one of them, a faint little spark of light less than a pixel wide. That tiny spark was everything. Every person, every dream, every city, every mountain and ocean, all compressed into one invisible shimmer of blue. Carl Sagan, the astronomer who helped inspire the picture, later described it as a reminder of how small, fragile and precious our world truly is in the cosmic scale. His words gave life to the image, and the pale blue dot became a symbol of perspective, a way for humanity to see itself from the outside. At that time, the Voyager image was the most distant view of Earth ever captured. The spacecraft was more than 6 billion kilometers away, so far that radio messages from it took hours to reach home. It was a lonely little machine at the edge of the sun's influence, looking back at the planet it had left behind. The sense of scale was overwhelming. The solar system itself seemed enormous, and Earth's faint glow in that final photograph felt like the smallest possible reminder of home. People who saw it were struck by both wonder and sadness, realizing that every war, every celebration, every joy and sorrow that had ever happened took place on that minuscule dot. But now, more than 3 decades later, humanity has built a new eye in the sky, one far more powerful than anything that existed in Voyager's time, the James Webb Space Telescope, launched in the early years of the 21st century, has given us a view of the universe that makes even the pale blue dot seem almost large in comparison. Where Voyager showed the smallness of Earth within the solar system, Webb has revealed the smallness of the entire solar system within the endless sweep of the cosmos. Its deep space images reach so far back in time and distance that even our sun and its planets become almost meaningless specks in the grand design of the universe. When the Webb telescope took its first deep field image, it aimed at a tiny section of sky, so small that if you held a grain of sand at arm's length, that grain would cover it. Yet within that minuscule patch of darkness, the telescope saw thousands of galaxies, each containing hundreds of billions of stars and perhaps countless planets. The image, shimmering with points of light that looked like distant jewels, was not showing stars but entire galaxies, each one an island of suns and worlds. Compared to that vision, the pale blue dot of Earth becomes so faint that it is almost impossible to grasp. In Voyager's picture, Earth was a single pixel. In Webb's view, even a single pixel represents clusters of galaxies that stretch across unimaginable distances. Humanity's home, which once seemed small but still significant in the void, now appears to vanish completely when placed beside the immensity that Webb reveals. It is as if the pale blue dot has dissolved into cosmic dust, blending into the infinite backdrop of time and space. This change in perspective is more than just a matter of better technology. It is a transformation in how we understand our existence. In 1990, the pale blue dot taught people humility. It showed that Earth was not the center of the universe, but a fragile speck floating in the dark. In the era of the Webb telescope, that humility deepens into something even greater: awe. The telescope's mirrors are so sensitive that they can capture light that has travelled for more than 13 billion years, reaching us from the first galaxies that formed after the birth of the universe. That means when we look at Webb's deep space images, we are seeing ancient light that began its journey long before Earth even existed. So, while Voyager looked back at a small blue spark from billions of kilometers away, Webb looks outward across the cosmic ocean and shows that there are billions of other sparks, other galaxies, each filled with their own worlds. The contrast is staggering. Voyager's image made us feel small. Webb's images make us feel almost non-existent. Yet within that nothingness, there is a strange beauty, a sense that even the smallest world holds meaning because it is part of something infinitely grand. When Carl Sagan wrote about the pale blue dot, he asked people to remember that this was our only home, the only world we have ever known. His words were a plea for kindness, for the recognition that the divisions among nations and peoples were trivial compared to the vastness of space. Today, looking at Webb's deep fields, those words seem more urgent than ever. Because if Voyager's picture showed how small we were, Webb's pictures show how rare we are. Out of all the galaxies, stars, and nebula stretching to the edge of time, we still know of only one tiny dot where life exists. The pale blue dot was an image of reflection. It looked back at Earth. The Webb telescope, on the other hand, looks forward, out into the past of the universe. But in a strange way, both images tell the same story. They are about perspective, about learning to see ourselves not as the centre of everything, but as a fleeting part of something much larger. Voyager showed that our planet was a speck in a solar system surrounded by darkness. Webb shows that even that solar system is part of a single galaxy among trillions. Each step in exploration expands the scale of what we can see, and each expansion makes us seem smaller. In the time of Voyager, humanity was just beginning to explore the outer planets. The spacecraft had shown us the swirling storms of Jupiter, the icy rings of Saturn, and the distant moons that orbited those giants. For most people, those images were the farthest they could imagine going. The solar system seemed endless. But as Webb peers across billions of light years, those same planets, once thought distant, now seem almost next door. The boundary of the solar system becomes a tiny bubble compared to the cosmic web of galaxies that fill the universe. In the pale blue dot image, the space between planets looked empty, vast, and silent. But Webb's infrared eyes reveal that the darkness is not truly empty at all. It is filled with faint light from galaxies so far away that their glow has stretched into invisible wavelengths. Every point of nothingness, every black patch of sky, hides countless suns and worlds beyond our sight. The universe is not a void, it is a boundless sea of creation, too immense for the human mind to fully understand. And yet, within that immensity, Earth continues to shine as that same small dot of blue light. Nothing about the planet has changed, only our vision has expanded. From Voyager's perspective, Earth was small but still visible, a gentle glimmer among rays of sunlight. From Webb's perspective, the very concept of small takes on a new meaning, because if we were to place Earth next to one of the galaxies in Webb's deep field, it would be invisible, utterly lost. Our entire solar system would vanish inside the faintest smudge of light. Even the Milky Way, our home galaxy, becomes just one among billions, a single thread in an infinite cosmic tapestry. This realization can feel unsettling. For centuries, humanity has sought to understand its place in creation. Ancient astronomers once believed Earth was the center of all things. Later, people learned that Earth orbited the Sun, and that the Sun was just one star among many. Voyager's pale blue dot was another step in that journey, showing that even our planet was just a point of light in the void. Now Webb has taken that perspective to its ultimate extreme. Not only is Earth a speck, but even the entire visible universe may be just a tiny fragment of a much larger reality. The Webb telescope's vision reaches so far that it may one day reveal the faint glow of the first stars ever formed. It has already captured galaxies so distant that their light has been stretched by the expansion of the universe for over 13 billion years. The colours we see in its images are not just artistic, they represent the physical stretching of light, the redshift caused by the universe's growth. In those galaxies, we're seeing the earliest structures that gave birth to stars, planets, and possibly even life. To look at such images and then think of the pale blue dot is to experience a dizzying sense of contrast between the near and the infinite. And yet, there is a deep connection between them. Both images, the pale blue dot and Webb's deep fields, are acts of looking back. Voyager looked back at its origin, while Webb looks back in time. Both are reminders that the universe is not static. It is a story, one still unfolding. Voyager's journey beyond the solar system is a story of human curiosity reaching outward. Webb's mission is the continuation of that same curiosity, reaching farther still into the beginning of everything. The pale blue dot remains powerful because it speaks directly to human emotion. It is not just a scientific image. It is a mirror held up to humanity's face. People look at it and feel a mix of pride and humility. Pride that we could send a machine so far, and humility that from that distance, everything we have ever known becomes invisible. The Webb images, on the other hand, evoke a different kind of emotion. They do not show home, they show the vastness that surrounds home. They make people wonder about what else might exist, about what distant worlds circle the stars in those faraway galaxies. Somewhere, in all that immensity, there might be other pale blue dots, other planets with oceans and skies, maybe even other beings looking up at their own night skies and asking the same questions. Voyager's camera captured the light that reflected off Earth's clouds and seas. Webb's mirrors capture the ancient glow of galaxies that existed before the sun was born. One shows the present seen from afar, the other shows the past seen from the present. Together they form a bridge across time and space, connecting the smallness of our world to the vastness of the universe. The more we see, the more we understand that the pale blue dot is not just a single image. It is a symbol of every world that could ever exist, every spark of light that dares to shine in the dark. It is striking to think that the pale blue dot, a single pixel captured by an old spacecraft in 1990, continues to inspire people even after more than 30 years. In an era of high-resolution telescopes and cosmic discoveries, that faint image still holds unmatched emotional power. Technology can show us billions of galaxies, but it cannot easily recreate the feeling of seeing our entire existence reduced to a single point of light. Webb's images are grand and magnificent, but Voyager's image is intimate. It reminds us that we're not only observers of the universe, but part of it. As Webb continues its work, scientists will use it to look for exoplanets, worlds around other stars that might resemble Earth. Some of those planets may turn out to be pale blue dots of their own, orbiting distant suns. Perhaps one day, another civilization will send its own Voyager out into the cosmos and look back, seeing its home as a single point of light just as we did. In that moment, they too will feel the same mixture of awe and humility that we felt when we saw our own planet from afar. The pale blue dot in that sense is not just a picture, it is a universal truth. No matter who looks, no matter where they are, they will see that all life, all meaning, is contained within something unimaginably small against the backdrop of infinity. When we compare the pale blue dot to Webb's deep space views, we are really comparing two kinds of understanding. One comes from looking back at what we know, and the other from looking outward at what we do not. Both are essential. Voyager showed that distance brings clarity. It allowed us to see ourselves from the outside. Webb shows that depth brings wonder. It allows us to see the vastness of everything beyond. Together, they remind us that perspective is the greatest gift of exploration. The tiny dot of light in Voyager's image might seem fragile, but it contains everything that makes life meaningful. The galaxies in Webb's images might seem unreachable, but they remind us that existence is far greater than we once believed. The contrast between them is what gives both images their power. The pale blue dot is personal. It speaks to the heart. Webb's view is cosmic. It speaks to the soul. And between the two lies the entire human experience, the desire to know, to explore, and to understand where we belong. Over the years, the pale blue dot has been printed in books, displayed in museums, and shared across generations. Children have grown up seeing it and feeling, perhaps for the first time, how small yet special their world is. Webb's images will likely have the same effect on future generations, showing them that beyond their skies lies a universe more immense than any dream. In a sense, Voyager and Webb are two chapters of the same story, the story of a species that refuses to stop asking questions. The pale blue dot was a farewell glance, a look homeward from the edge of the solar system. The Webb telescope, by contrast, is a gaze outward, toward the beginnings of time itself. Yet both views lead to the same conclusion, that humility and wonder are not opposites, they are companions. The more we see of the universe, the more we understand how precious our tiny world is. The pale blue dot showed us our smallness. Webb shows us our connectedness. Every shaft of light in Voyager's photograph, every faint swirl in Webb's deep fields, tells the same cosmic truth, that light travels, endures, and carries stories. The light from Earth that Voyager captured was reflected sunlight, bouncing off clouds and oceans before reaching a distant camera. The light that Webb captures has travelled across billions of years, surviving the birth and death of stars, the growth of galaxies, and the expansion of space itself. Both kinds of light remind us that to exist is to shine, even if only briefly. The pale blue dot may be a single pixel, but it represents an entire world of thought, emotion, and memory. Webb's galaxies may be countless, but they remind us that creation itself is endless. Between the dot and the deep field lies the entire range of human understanding, from knowing who we are to wondering what else might be. Every time we look at those images, we're reminded that perspective is not just about distance or detail, it is about meaning. The Voyager photograph was taken from 6 billion kilometers away, but its message reaches far beyond that distance. It tells us that even from the edge of the solar system, home can still be seen. Webb's images stretch across 13 billion years, but their message is the same, that even in the farthest reaches of time and space, light still finds a way to reach us. In both cases, what we see is not just light, it is the story of everything that ever was and everything that might be. When the Voyager camera turned for that final look, no one could have known that decades later, another instrument would take humanity's vision even farther. Yet the two are forever linked. The pale blue dot began the journey of seeing ourselves from the outside. Webb continues that journey by showing us that even the vast universe outside still reflects something of ourselves. Every galaxy, every star, every distant glow is a reminder that the same physical laws, the same cosmic story flows through everything. At the farthest edges of the observable universe, in a realm so distant that its light has been travelling toward us for over 13 billion years, the James Webb Space Telescope has uncovered galaxies that were born not long after the universe itself came into existence. These galaxies formed just a few 100 million years after the Big Bang, a blink of an eye in cosmic time, and their discovery has completely changed how humanity understands the early history of the cosmos. For generations, astronomers have looked into the night sky and wondered what the universe looked like in its youth, but until recently, even the most powerful telescopes could only offer faint clues. Now, for the first time, we can see those first ancient galaxies as they truly were, glowing faintly across the endless sea of time and distance, their light stretched by the expansion of space into long, gentle wavelengths of infrared radiation that only Webb's sensitive instruments can detect. In the earliest moments after the Big Bang, which happened around 13.8 billion years ago, the universe was a chaotic storm of energy and subatomic particles. There were no stars, no planets, no galaxies, only darkness filled with a glowing fog of hot plasma. As the universe expanded and cooled, that fog began to thin out, allowing the first atoms to form. This period, often called the Cosmic Dark Ages, lasted for hundreds of millions of years. It was during this mysterious time that gravity began its quiet work, slowly pulling together clouds of hydrogen and helium gas into denser regions that would eventually ignite into the first stars. Those stars were unlike anything that exists today, enormous, short-lived giants that burned fiercely and died young, scattering their newly forged elements into space. From those remains, the first galaxies began to take shape, forming glowing islands of stars in a vast and otherwise empty sea. For decades, astronomers dreamed of being able to see those first galaxies, but the light from such ancient objects was too faint and too redshifted for previous telescopes to capture. The Hubble Space Telescope, though revolutionary in its time, was not sensitive enough to peer back into that first epoch of creation. Hubble could see galaxies that formed a few billion years after the Big Bang, but not the ones that existed only a few 100 million years after it. That gap, the earliest period of galactic formation, remained one of the great mysteries of astronomy. When the James Webb Space Telescope was launched, it was built specifically to close that gap. With its massive gold-coated mirror and its ability to detect infrared light with incredible precision, Webb was designed to see through the cosmic dust and peer farther back in time than any instrument before it. As soon as Webb began its scientific mission, astronomers aimed it toward a patch of sky that, at first glance, appeared almost completely empty. It was an area so small that you could cover it with a grain of sand held at arm's length. Yet in that tiny speck of darkness, Webb's instruments revealed thousands of galaxies, some so faint and ancient that their light had begun its journey when the universe was less than 500 million years old. To put that into perspective, if the entire history of the universe were compressed into a single year, these galaxies would have appeared in the first week of January, while our Sun would not be born until late August. The light from those early galaxies had travelled across space for more than 13 billion years before finally reaching Webb's mirrors, allowing humanity to look back to a time when galaxies were still forming their first generations of stars. What makes these discoveries even more astonishing is how surprisingly mature some of these early galaxies appear to be. Astronomers had expected the first galaxies to be small, irregular and chaotic. loose gatherings of stars still in the process of forming. Instead, Webb found galaxies that seemed far more developed than anyone had predicted, containing large numbers of stars and even hints of organized structure. This suggests that galaxy formation happened much faster than models had assumed. In other words, the universe wasted no time in building its first grand structures. Some galaxies, visible as faint red smudges in Webb's images, existed just 300 million years after the Big Bang, meaning they formed when the universe was less than 3% of its current age. The discovery of these ancient systems has forced scientists to rethink how quickly matter gathered together and how rapidly the first stars ignited. At the heart of this new exploration are Webb's powerful instruments, such as the near-infrared camera, NIRCam, and the near-infrared spectrograph, NIRSpec. These devices can not only detect faint light, but also measure its wavelength precisely, revealing how much it has been stretched by the expansion of the universe. This stretching, known as redshift, acts like a cosmic time machine. The higher the redshift, the farther back in time the light originated. Some of the galaxies Webb has observed show redshifts greater than 13, meaning their light began its journey when the universe was only a few hundred million years old. Before Webb, astronomers had only seen galaxies with redshifts up to around 10, so these new detections represent a major leap in our ability to see the early universe. Each of these discoveries carries profound implications for our understanding of cosmic history. When astronomers study these first galaxies, they are not just looking at distant objects, they are witnessing the very process of cosmic creation. The stars within those galaxies produce the first heavy elements such as carbon, oxygen and iron, which would later become the building blocks for planets, life, and even human beings. The ultraviolet light from those early stars helped ionize the universe, clearing away the fog that had filled space since the Big Bang and making the cosmos transparent to light. In this sense, Webb is not only revealing ancient galaxies, but also uncovering the moment when the universe first began to shine. One of the most fascinating aspects of Webb's observations is how they connect the distant past to the present. The galaxies that Webb sees at the edge of time are the ancestors of the galaxies we see today. Over billions of years, those small primitive systems merged and evolved, forming the massive spiral and elliptical galaxies that populate the modern universe. Even our own Milky Way likely traces its lineage back to tiny protogalaxies like the ones Webb has found. In a way, when we look at those faint red galaxies, we are looking at our own distant relatives, the ancient forebears of the cosmic structures that would eventually give rise to our Sun, our planet, and all of us. What makes this realization so humbling is how young our solar system appears in comparison. The galaxies Webb is observing were already shining when the universe was just a few 100 million years old. Our Sun, by contrast, did not form until about 9 billion years later. That means the light from those first galaxies had been traveling through space for 9 billion years, before our solar system even existed. By the time our planet formed, the universe had already gone through countless cycles of star birth and death, galaxy mergers, and cosmic evolution. Our entire solar system, everything we know and see, is a late arrival in an ancient universe that had already been busy creating and transforming itself for eons. When scientists look at these distant galaxies, they are not just counting stars or measuring redshifts. They are reading the universe's autobiography, written in light. Each faint glow is a chapter from the beginning of everything, preserved across unimaginable stretches of time. Some of the light reaching Webb today left its source so long ago that the galaxies which emitted it may have already merged, changed shape, or disappeared entirely. Yet their light endures, a message from the dawn of time whispering the story of creation across the vast emptiness of space. The colours that Webb detects tell astronomers much about the physical conditions in those early galaxies. The faint red glow in its images is not the colour of the galaxies themselves, but the result of cosmic expansion. As space stretches, it lengthens the wavelength of light, turning the originally blue or ultraviolet light from young, hot stars into deep infrared tones. By analysing this stretched light, scientists can estimate the age, temperature, and chemical composition of these distant galaxies. Some of the earliest ones appear to contain mostly hydrogen and helium, the simplest elements created in the Big Bang, with only tiny traces of heavier elements. This confirms that these galaxies were indeed among the first, still untouched by multiple generations of star formation. In a few of these ancient galaxies, Webb has even detected patterns of light that suggest the presence of dust, a sign that some of the first stars had already lived, died, and exploded in supernovae, enriching their surroundings with new elements. This is astonishing because it implies that the cycle of birth and death among stars began very early, within just a few 100 million years of the Big Bang. Those first supernova explosions seeded the cosmos with carbon, nitrogen, and other ingredients essential for life. In that sense, Webb's discovery is not just about galaxies, it is about the origin of everything that would one day make life possible. As Webb continues to explore, it is mapping out a timeline of cosmic evolution, showing how galaxies grew from small, irregular blobs into the grand spirals and clusters we see today. The data suggests that the universe was already teeming with structure much earlier than expected. Clusters of galaxies, some appearing only a few 100 million years after the Big Bang, hint that matter gathered under gravity far more efficiently than previous models predicted. These findings are prompting cosmologists to revisit their theories about dark matter, the mysterious substance that makes up most of the universe's mass. Perhaps dark matter played a stronger role in shaping early galaxies than once thought, or perhaps our understanding of cosmic physics is still missing something fundamental. The sheer distances involved in these observations are beyond human comprehension. Light from some of these galaxies has travelled more than 13 billion light-years to reach us, meaning Webb is seeing them as they existed when the universe was less than 5% of its current age. Space itself has expanded tremendously during that time, so the actual distance to those galaxies today is even greater, perhaps over 30 billion light-years. Yet thanks to the finite speed of light, Webb gives us the power to look back through time as if we were travelling into the past, watching the first sparks of cosmic dawn ignite against the darkness. What Webb has shown is that the early universe was far more active, complex and colourful than anyone had imagined. Instead of a slow and gradual emergence of galaxies, it seems there was a rapid burst of creation, a cosmic springtime when stars and galaxies bloomed across the young universe in astonishing numbers. In one small patch of sky, Webb's deep field images reveal thousands of galaxies, each containing billions of stars, stretching as far as the telescope can see. The sheer abundance of light from such a tiny region suggests that the entire universe is filled with far more galaxies than previous estimates, perhaps hundreds of billions more. If every faint speck of light in Webb's view represents a galaxy, then the total number of stars in the cosmos is beyond anything our minds can truly grasp. This realization also reshapes our understanding of cosmic time. To the universe, a few 100 million years is like a heartbeat. To humanity, it is an eternity beyond imagination. Yet when we peer into Webb's images, we see that those first galaxies were already forming, already shining, already weaving the structure of space that would eventually lead to us. It reminds us that the universe has been evolving for eons before we arrived and will continue to change long after we're gone. Our place in this grand story is brief, but through instruments like Webb, we're able to witness the beginning of everything, a privilege that no generation before ours has ever had. Among the many galaxies Webb has detected, some stand out as particularly intriguing. Astronomers have identified candidates with redshifts greater than 13, which means their light was emitted only about 300 million years after the Big Bang. One galaxy, labelled Sears 93316, may have formed just 235 million years after the beginning of time. If confirmed, it would be the most distant and ancient galaxy ever observed. Its light has travelled across space for over 13.5 billion years to reach us. The fact that such a system existed so early challenges everything we thought we knew about how quickly galaxies could assemble their stars and gas. It suggests that the early universe was capable of producing complex structures almost immediately after its birth. The study of these early galaxies also offers insight into one of the universe's greatest transitions, the end of the cosmic dark ages. During this period, the universe was filled with neutral hydrogen that absorbed light, making it opaque. The emergence of the first stars and galaxies flooded space with ultraviolet radiation that rionized the hydrogen, transforming the universe from opaque to transparent. Webb's observations help pinpoint when and how this rionization happened. By studying the light from ancient galaxies and how it interacts with surrounding gas, astronomers can trace the timeline of this transformation, a moment when the universe truly lit up for the first time. Each observation from Webb requires extraordinary care and patience. The telescope must collect faint light for many hours or even days to build up enough signal to detect these distant galaxies. The resulting images are then carefully analysed, with scientists checking every pixel to ensure that what they see is real and not an artifact of noise or interference. Sometimes, a tiny red dot in Webb's data can represent an entire galaxy of billions of stars, its light dimmed and stretched by unimaginable distances. These detections are confirmed by spectroscopy, which breaks the light into its component colours and measures its exact redshift, giving astronomers a precise estimate of the galaxy's age. The discovery of ancient galaxies has also inspired new questions about what lies even farther beyond. If Webb can see galaxies that formed just a few 100 million years after the Big Bang, could there be others that formed even earlier, perhaps within the first 100 million years? Theoretically, the very first stars, often called population 3 stars, should have formed during that time, but none have been directly observed yet. These first stars would have been massive and short-lived, leaving behind black holes or supernova remnants that may still exist today. Webb's instruments might one day detect the faint glow or indirect effects of those primordial stars, offering the first direct glimpse into the universe's ultimate beginnings. In addition to studying galaxies, Webb's findings are helping scientists understand how supermassive black holes formed so early in cosmic history. Some of the galaxies Webb has detected already seem to host black holes with millions of times the mass of the Sun, which is astonishing given how little time had passed since the Big Bang. This raises deep questions about how such enormous objects could form so quickly. Perhaps they were born from the direct collapse of massive gas clouds, rather than from smaller stars merging over time. Whatever the case, Webb's data will help unravel this cosmic mystery and reveal how black holes influence the growth of galaxies throughout the universe's history. What makes all of this so awe-inspiring is not just the scientific achievement, but the perspective it gives humanity. To think that the light now reaching Webb began its journey when the universe was only a few 100 million years old, long before our Sun, Earth, or even our galaxy existed, is to confront the immensity of time and space. Every photon captured by Webb is a survivor of an epic voyage across billions of years, carrying with it the story of creation itself. Through these discoveries, we are reminded that everything we are, every atom in our bodies, was once part of that same ancient light, forged in the hearts of the first stars that Webb now reveals. The more Webb looks, the more it finds. Each new deep field reveals galaxies even fainter and farther than before, extending our vision ever closer to the moment of the Big Bang. It is as if the universe itself is opening its ancient diary, page by page, showing us what it was like to be young. Every tiny point of light in Webb's images represents an entire galaxy, each one containing billions of stars, many of which may have planets orbiting them. Somewhere among those countless worlds, perhaps the first seeds of life began to form long before our own planet existed. The discovery of ancient galaxies is therefore not just a look into the past, it is a mirror showing us where we come from, and perhaps where others may have come from too. Even as Webb continues to push the boundaries of observation, it has already accomplished what no telescope before it could. It has allowed humanity to witness the universe's first light, to see the galaxies that formed at the dawn of time, and to understand that our Sun, which feels so ancient to us, is in truth a newcomer in a cosmic story that began long before. These ancient galaxies, small and distant though they appear, are the original architects of everything that followed. They are the first sparks in the great cosmic chain that ultimately led to us. Their light, after travelling for more than 13 billion years, now reaches our eyes through the delicate mirrors of a telescope orbiting far from Earth. A telescope built by beings who, countless generations later, came to wonder about their own beginnings and found the answer written across the sky. Measuring the cosmic tapestry is one of the most astonishing tasks ever attempted by the human mind. It is the effort to understand not only where we are in the universe, but how vast that universe truly is. Since the first time a curious observer raised their eyes toward the stars, people have wondered how big everything really is. But now, with the help of the James Webb Space Telescope, humanity has reached a new level of understanding, one that stretches the limits of imagination and brings us face to face with the immensity of existence itself. The Webb telescope, floating silently in the cold darkness about 1.5 million kilometers from Earth, has become our greatest tool for exploring the endless patterns of galaxies that fill the cosmos. With its golden mirrors and advanced instruments, It allows astronomers to measure the size, distance, and number of galaxies that make up what we call the observable universe. The idea of measuring the universe might sound impossible at first. After all, how can we measure something that seems to have no edge, no limit, and no end? Yet astronomers do not need to measure everything. They only need to measure what we can see, the part of the cosmos whose light has had enough time to reach us since the beginning of time. Light travels at a finite speed, about 300,000 kilometers per second, which means that when we look into space, we're actually looking back in time. The farther away a galaxy is, the older the light we receive from it. By using Webb-sensitive instruments, scientists can study light that has traveled for more than 13 billion years from galaxies that formed not long after the birth of the universe itself. This makes the Webb telescope a kind of time machine, one that lets us witness the earlier stages of creation. Astronomers use it to capture faint, stretched light from ancient galaxies that have been moving away from us since the universe began expanding. That expansion means that the light's wavelength has been stretched by what scientists call redshift. The greater the redshift, the farther the galaxy. Webb's powerful infrared instruments were designed specifically to detect this redshifted light, which is invisible to the human eye but holds the key to measuring the distance to these faraway objects. By studying that light, scientists can calculate not just how far the galaxy is now, but how long ago the light began its journey toward us. To understand how large the observable universe is, astronomers combine data from Webb with that from earlier telescopes, such as Hubble and ground-based observatories. These combined measurements help refine the scale of the cosmos. The observable universe stretches about 93 billion light-years across, meaning that the most distant regions we can see are about 46.5 billion light-years away in every direction. But that number is constantly being re-examined as telescopes like Webb reveal more galaxies farther and fainter than we ever thought possible. Each new image taken by Webb deepens our knowledge of the cosmic structure, the intricate web of galaxies and dark matter that fills space. This cosmic web is not evenly spread. It is a vast network of filaments and clusters where galaxies gather, separated by enormous voids that contain almost nothing. Astronomers sometimes compare it to a sponge or a web stretched across unimaginable distances. But to measure this structure accurately, they must rely on light itself as their ruler. Webb's instruments, such as its near-infrared camera and mid-infrared instrument, can detect the faintest traces of light from the earliest galaxies. Each tiny speck of light on a Webb image could be an entire galaxy containing billions of stars. When Webb took its first deep-field image, a single snapshot revealed thousands of galaxies in a tiny area of sky, smaller than a grain of sand held at arm's length. That image alone showed astronomers how rich and crowded the universe is. But more importantly, it gave them data to estimate how many galaxies exist across the entire observable universe. If a patch that small contained thousands of galaxies, then scaling that up to the whole sky means that there could be hundreds of billions, or even more than 1 trillion galaxies in total. Each of these galaxies may hold billions of stars, and many of those stars may host planets. The numbers become so vast that they go beyond easy comprehension, yet astronomers continue to refine these estimates with Webb's data. One of the greatest challenges in measuring the universe is accounting for how much it has expanded over time. The universe has been stretching since it first began with the event we call the Big Bang, about 13,800,000,000 years ago. Because of that expansion, galaxies that were once closer together are now separated by vast distances. Webb helps scientists trace this expansion by observing galaxies at different stages of history. When astronomers look at galaxies that existed only a few 100,000,000 years after the Big Bang, they can compare their light with that of closer, more recent galaxies to see how fast the universe has been stretching. This expansion rate is known as the Hubble constant, named after Edwin Hubble, the astronomer who first discovered that galaxies are moving away from us. But even today, the exact value of the Hubble constant is still uncertain. Different methods produce slightly different results, and Webb is now playing a crucial role in solving this cosmic puzzle. Its detailed observations of distant galaxies and the ancient light from stars within them help astronomers refine their measurements and bring us closer to understanding how quickly the universe is growing. The light that Webb collects carries with it a story written across billions of years. By breaking down that light into its individual colours, scientists can learn about the composition, temperature, and motion of distant galaxies. They can tell what kinds of stars fill them, what elements those stars have created, and how old the galaxies are. In this way, Webb does not only measure distances, it also builds a map of cosmic history, showing how the first small galaxies grew and merged to form the vast spirals and clusters we see today. Each faint glimmer of light adds another thread to the great tapestry of the cosmos, revealing how structure and order emerge from the chaos of the early universe. One of the most fascinating things about Webb's work is how it turns invisible light into knowledge. Much of the universe cannot be seen with ordinary eyes because its light has been stretched beyond the visible spectrum into the infrared. That is why Webb's mirrors and instruments are designed to detect heat rather than ordinary light. Every galaxy, even the faintest, gives off infrared radiation that tells astronomers where it is and how long its light has travelled. To ensure accuracy, Webb's sensors are kept colder than any place on Earth, shielded from heat and sunlight by its enormous sunshield. That careful design allows it to detect the faintest signals ever captured from the dawn of time. When scientists measure galaxies, they look at three key things: their size, their distance, and their brightness. Size tells them how big a galaxy is and how much matter it contains. Distance tells them how far away it is, which helps determine how long ago its light was emitted. Brightness, meanwhile, reveals how much energy the galaxy gives off and how many stars it holds. But none of these things can be measured directly. Instead, astronomers use light as a guide. The farther away a galaxy is, the dimmer and redder its light becomes due to expansion. By comparing the light from different galaxies, Webb allows scientists to build a scale of cosmic distances, stretching from nearby galaxies like Andromeda to the faint smudges at the edge of visibility that may be among the first galaxies ever formed. The precision of these measurements is astounding. Webb can detect differences in light that are smaller than a fraction of a nanometer, a scale so tiny that it defies everyday sense. Each measurement helps scientists refine their models of how galaxies form and evolve. They can estimate how fast stars were being born in the early universe, how heavy elements spread through space, and how clusters of galaxies gathered into the cosmic web we see today. To measure the number of galaxies, astronomers often rely on statistical methods. They take deep images of small patches of the sky, count how many galaxies they see in each patch, and then multiply that number by the total area of the sky. This method gives a rough but powerful estimate of how crowded the universe is. Earlier telescopes suggested that there might be about 200 billion galaxies in the observable universe, but Webb's data may push that number far higher. Some astronomers now suspect that there could be more than 1 trillion galaxies, many of them so faint and distant that even Webb can barely detect them. Each time Webb looks deeper into space, it finds more galaxies than anyone expected. Another important aspect of measuring the cosmic tapestry is understanding how galaxies are arranged. They are not scattered randomly but form patterns shaped by gravity. Galaxies cluster together into groups and superclusters, which themselves are connected by long filaments of dark matter. Between these filaments lie enormous empty regions known as voids, stretching for hundreds of millions of light years. Webb's detailed observations help scientists map these structures in greater detail, revealing how matter flows across cosmic space and how gravity has sculpted the universe over billions of years. Webb's measurements also touch on one of the most mysterious subjects in science: dark matter and dark energy. Together, these unseen forces make up about 95% of the universe, yet they cannot be observed directly. By studying how galaxies move and how their light is bent by gravity, Webb helps astronomers infer the presence of these invisible components. The bending of light, called gravitational lensing, acts like a natural telescope, magnifying distant galaxies behind massive clusters of matter. When Webb captures such events, it can study galaxies that would otherwise be far too faint to detect. These observations not only extend our reach into the depths of space, but also allow scientists to measure how much unseen mass lies between us and those faraway objects. Every time Webb observes a lensed galaxy, it measures how light has been distorted by gravity. By analysing that distortion, scientists can calculate the distribution of mass in the universe and refine their models of dark matter. Similarly, by tracking how galaxies move apart over time, they can measure the influence of dark energy, the mysterious force driving the accelerated expansion of the universe. In this way, Webb's work extends far beyond counting galaxies. It helps us understand the fundamental forces shaping reality itself. The precision with which astronomers can now measure the cosmos is the result of centuries of progress. Long before Webb, Early astronomers such as Galileo, Kepler, and Newton laid the groundwork for cosmic measurement. Later, Edwin Hubble's discovery that galaxies are moving away from us showed that the universe is expanding. The Hubble Space Telescope then extended that vision by capturing light from galaxies billions of light years away, but Webb's technology surpasses them all, reaching farther back in time and revealing galaxies that existed when the universe was still in its infancy. These discoveries have changed how humanity sees its place in the cosmos. What once seemed an empty void is now known to be filled with countless worlds. Our own galaxy, the Milky Way, is just one of billions, each a glittering island in a boundless ocean of stars. Measuring that ocean, even with the best instruments ever built, is like trying to count the grains of sand on every beach on Earth. Yet Webb brings us closer than ever before to understanding the scale and structure of that grand design. Astronomers working with Webb often describe their sense of awe at the telescope's abilities. They point to images where galaxies appear as faint smudges, their light stretched and reddened by the passage of time. Some of those galaxies existed when the universe was less than 500 million years old, meaning that Webb is showing us scenes from a time before our Sun, Earth, or even the Milky Way existed. These images provide not only data but perspective, reminding us that our cosmic story is just one small part of a much larger whole. The task of measuring the universe is ongoing and will likely never be fully complete. Every new observation reveals more complexity. The galaxies Webb observes today may one day be joined by even fainter ones revealed by future instruments. But for now, Webb stands as our best window into the ancient past, our finest tool for unraveling the tapestry of space and time. With each measurement, scientists refine their understanding of how everything fits together, from the smallest particles of light to the largest clusters of galaxies. To calculate cosmic distances with Webb, astronomers use several methods, each suited to different ranges. For nearby stars and galaxies, they might use parallax, observing how an object appears to shift position as Earth moves around the Sun. For more distant galaxies, they use the redshift of light as a measure of how much the universe has expanded since that light was emitted. In the most distant regions, where light is faint and ancient, Webb's infrared sensitivity is crucial. By comparing the patterns of light from those galaxies with theoretical models, astronomers can estimate their age, distance, and brightness. These measurements are then combined to create three-dimensional maps of the universe, where every point represents a galaxy, and every colour encodes its distance and history. What makes Webb so effective at this is its ability to see both faint and bright objects with incredible clarity. Its large mirror collects far more light than previous telescopes, allowing it to capture distant galaxies in remarkable detail. Its instruments can separate light into hundreds of wavelengths, revealing subtle differences that tell scientists exactly what they are looking at. By analysing these patterns, they can determine not just how far away something is, but how it has changed over time. When astronomers look at Webb's images, they see not only galaxies but layers of history. The nearest galaxies show what the universe looks like today, full of large spiral systems and mature stars. Farther away, galaxies appear smaller and less organised, showing what the cosmos looked like billions of years ago. And beyond that, at the very edge of visibility, Webb detects the faint glow of the first galaxies ever formed. These earlier systems are tiny and irregular, but they represent the seeds from which all later structures grew. By measuring their light, astronomers can trace the evolution of cosmic structure, from the first flicker of starlight to the grand tapestry we see now. Even as Webb measures the distances to these ancient galaxies, it also helps refine our understanding of time itself. The universe is not static. It changes constantly. Galaxies collide and merge, stars are born and die, and the expansion of space stretches the distance between everything. Each observation Webb makes adds a new piece to this puzzle, helping us understand how fast time moves on cosmic scales and how the universe has aged since its beginning. Light from the farthest galaxies Webb observes began its journey more than 13 billion years ago, but because space has expanded since then, those galaxies are now much farther away than they were when the light started travelling. Measuring that difference allows scientists to calculate both the rate of expansion and the age of the universe. It also helps determine how matter and energy have interacted over cosmic history. Some of these measurements even provide clues about the ultimate fate of the universe, whether it will expand forever, slow down, or someday collapse back upon itself. The discovery of planets beyond our solar system, called exoplanets, has revealed that our cosmic neighbourhood is only one among billions. And now, thanks to the James Webb Space Telescope, astronomers can finally look into the skies of these distant worlds, detect the gases in their atmospheres, and even search for signs of life's chemistry among the stars. In the early years of the 21st century, NASA's Kepler Space Telescope began a quiet revolution. Launched in the year 2009, Kepler's mission was to stare at a small patch of the Milky Way and record tiny dips in the brightness of stars. These small dips meant that a planet was passing in front of its star, blocking a little bit of its light. From those faint shadows, Kepler confirmed what astronomers had only dreamed of, that planets are common, even ordinary across the galaxy. By the time Kepler's mission ended in the year 2018, it had found more than 2,000 confirmed exoplanets and suggested the existence of tens of billions more. Although Hubble was not built to study exoplanets, it managed to observe the first exoplanet atmosphere in the early 2000s. In the year 2002, Hubble detected sodium in the atmosphere of a distant planet called HD 209458b. This was the first time humanity had ever identified a specific element in the air of another world. Later, Hubble revealed water vapour, methane and carbon dioxide on a few hot and giant exoplanets. But its instruments were not sensitive enough to see smaller Earth-like worlds. For that kind of detail, scientists needed a new kind of telescope, one that could see in infrared light, where the heat from stars and planets tells a deeper story. In its first year of operation, Webb began to examine the atmospheres of exoplanets with a precision that no telescope before it could achieve. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching us. Different gases absorb light at specific wavelengths, leaving behind a kind of fingerprint known as a spectral signature. By spreading that light into a spectrum, Webb can identify which gases are present: water vapour, methane, carbon dioxide, sulfur dioxide, or even complex organic molecules. One of Webb's earliest and most famous targets was a world called WASP-39b. This planet, discovered in the year 2011 by a ground-based survey called the Wide-Angle Search for Planets, or WASP, is located about 700 light-years away from Earth. WASP-39b is a type of exoplanet known as a hot Saturn, meaning it has roughly the same mass as Saturn, but orbits much closer to its star, completing one orbit in only 4 Earth days. Its atmosphere is heated to more than 900 degrees Celsius, hot enough to melt metals. When Webb turned its instruments toward WASP-39b, it made history. The telescope's near-infrared spectrograph, known as NIRSpec, and its near-infrared camera, or NIRCam, detected a variety of gases, including water vapour, carbon dioxide, carbon monoxide, and, for the first time ever on any exoplanet, sulfur dioxide. This was a breakthrough, because sulfur dioxide is not produced by the planet itself, but through a process called photochemistry, where high-energy radiation from the host star changes the molecules in the planet's atmosphere. This meant that Webb was not just detecting what gases were present, but was seeing chemistry in action on another world. It proved that exoplanet atmospheres could be dynamic and complex, shaped by the energy of their stars in ways similar to processes that happen in our own solar system. Webb's data on WASP-39b also revealed that the planet's atmosphere contained much more oxygen and carbon than scientists expected. This suggested that WASP-39b might have formed farther away from its star, in a region rich in icy materials, and then migrated inward over time. Such details help scientists understand how planets form and move in their systems, clues that also tell us how our own solar system came to be. Another remarkable world that Webb observed is K2-18b. This planet orbits a red dwarf star about 120 light-years away in the constellation Leo. It was first discovered by NASA's Kepler mission during its extended K2 phase in the year 2015. K2-18b is larger than Earth but smaller than Neptune, a type of planet often called a sub-Neptune. This kind of world does not exist in our solar system, making it especially interesting to study. Before Webb, Hubble had already hinted that K2-18b might have water vapour in its atmosphere, but Hubble's instruments could not confirm what else was there. When Webb observed K2-18b using its near-infrared spectrograph and its mid-infrared instrument, known as MIRI, the results surprised astronomers. Webb detected clear signs of methane and carbon dioxide, as well as possible traces of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is produced mostly by living organisms in the ocean, particularly microscopic plankton. While it is far too early to say that life exists on K2-18b, the presence of this molecule raises fascinating questions. The observation suggested that K2-18b might have a hydrogen-rich atmosphere surrounding a deep ocean. Scientists sometimes call such planets Hycean worlds, meaning ocean worlds with thick hydrogen atmospheres. If K2-18b truly has a global ocean beneath its clouds, it could potentially be a place where life might survive, protected from harsh starlight by its atmosphere. Webb's ability to detect these molecules on a planet so far away, over 1 quadrillion kilometers from Earth, marks one of the most extraordinary achievements in astronomy. Webb has also examined another hot giant world called WASP 96b, located about 1,150 light-years away. This exoplanet, discovered in the year 2014, is roughly half the mass of Jupiter, but orbits its star once every 3.5 days. When Webb observed it, the telescope's instruments detected a strong and unmistakable signature of water vapor in its atmosphere. The spectrum also revealed clouds and hazes, something earlier telescopes had missed. What made this result so striking was how clear the data were. For decades, astronomers had hoped to see such direct and detailed measurements, but Earth's atmosphere and the limitations of previous instruments made it almost impossible. Webb's location beyond the Moon's orbit and its advanced infrared sensors finally gave scientists the clarity they needed. The observation of WASP 96b's atmosphere became one of the first public demonstrations of Webb's power, and was included in the telescope's first set of scientific images released in July of the year 2022. Another interesting planet Webb has studied is WASP 17b, a huge gas giant located about 1,300 light-years away. It is more than 1.5 times the size of Jupiter, but has less than half its mass, making it a puffy planet with an extremely low density. In October of the year 2023, Webb detected silicon monoxide particles in its atmosphere, the first time such a compound had been seen in the clouds of an exoplanet. These particles likely formed from silicate grains, tiny pieces of sand-like material, that were lifted high into the atmosphere by strong winds and heat. Observing such details helps researchers understand how exotic weather systems work on distant worlds, where winds may blow at thousands of kilometers per hour and clouds are made not of water, but of molten rock. One of Webb's most dramatic capabilities is its precision in measuring carbon-bearing molecules. For example, in the case of the exoplanet HD 209458b, the same world first studied by Hubble, Webb's instruments were able to provide a much more detailed look. It confirmed the presence of carbon dioxide and found subtle patterns that revealed how the planet's atmosphere was layered. The amount of carbon dioxide detected helped scientists estimate the planet's overall composition and history of formation. The more carbon and oxygen a planet has, the more likely it formed farther out in its system where icy materials are common. This kind of data allows astronomers to piece together not just what exoplanets are like now, but how they came to exist in the first place. What makes Webb especially valuable is its ability to detect faint differences in light, differences smaller than 1 part in 10,000. This sensitivity allows it to see the smallest features in a spectrum that correspond to rare molecules. For example, in the case of WASP 39b, Webb detected sulfur dioxide in amounts so precise that scientists could calculate how much ultraviolet light the planet's atmosphere was receiving from its star. It was like watching a chemical laboratory operating under alien skies. In the broader view, Webb's discoveries are changing how we think about our place in the universe. For centuries, humanity believed that our solar system might be special, perhaps even unique. The Sun, the 8 planets, and their moons seemed to form a pattern unlike anything else we knew. But the thousands of exoplanets discovered by Kepler and the hundreds now being examined by Webb show that nature loves variety. There are planets larger than Jupiter that orbit closer to their stars than Mercury does to the Sun. There are small rocky planets that orbit red dwarfs with years lasting only a few Earth days. There are even planets that seem to float freely in space, without any star at all. Webb's infrared instruments are particularly good at studying planets around red dwarf stars, which are the most common type of star in the Milky Way. These stars are smaller and cooler than the Sun, which means their habitable zones, the regions where liquid water could exist, are much closer in. Because of this, planets orbiting red dwarfs pass in front of their stars more frequently, making them easier to study. One famous system of this kind is TRAPPIST-1, a red dwarf located about 40 light-years away in the constellation Aquarius. The TRAPPIST-1 system contains 7 rocky planets, all roughly the size of Earth, and 3 of them lie within the star's habitable zone. Webb has begun studying the TRAPPIST-1 worlds in detail, starting with TRAPPIST-1b and TRAPPIST-1c. The telescope's first results show that TRAPPIST-1b does not have a thick hydrogen atmosphere. Instead, it may be a bare rocky planet more like Mercury or Venus. This kind of information is crucial because it helps scientists understand which planets might actually be capable of supporting life. In the future, Webb will continue observing the other TRAPPIST-1 planets, especially those in the middle of the system, where temperatures could allow water to exist on the surface. The method Webb uses for these studies is called transmission spectroscopy. When a planet crosses its star, the starlight that passes through the atmosphere is changed by the gases it meets. By comparing the starlight before and during the transit, scientists can tell which wavelengths are absorbed and which are not. Each molecule has its own distinct pattern, almost like a barcode, allowing astronomers to identify it with great confidence. Webb's high-resolution instruments can measure these patterns across a wide range of infrared wavelengths, far more precisely than Hubble ever could. Beyond transmission spectroscopy, Webb also performs what is called emission spectroscopy, where it observes the planet as it moves behind its star. When the planet disappears, the total light from the system drops slightly, allowing scientists to measure how much light was coming from the planet itself. This technique reveals the planet's temperature, heat distribution, and sometimes even weather patterns. For example, by observing a planet's infrared emission at different points in its orbit, Webb can detect hotspots or clouds that shift as the planet rotates. This gives us the first glimpses of alien meteorology. These discoveries are not only fascinating but also deeply humbling. They show that the processes that shaped our solar system, the formation of planets from disks of gas and dust, the migration of giant worlds, the chemistry of atmospheres, are happening everywhere. Webb's observations demonstrate that the ingredients for life, such as water and carbon-based molecules, are widespread throughout the cosmos. The universe, it seems, is not barren but rich in diversity, filled with countless variations of planetary systems. Each of Webb's discoveries adds a new piece to a vast puzzle. The detection of water vapor on WASP-96b tells us that hydrogen and oxygen can combine in the atmospheres of giant planets. The sulfur dioxide on WASP-39b shows that ultraviolet light from a star can drive complex chemistry. The methane and carbon dioxide on K2-18b hint at the possibility of life-friendly oceans beneath thick skies. Even the lack of certain gases, like in TRAPPIST-1b, teaches us about how planets lose or retain their atmospheres. Astronomers are now beginning to imagine what Webb might find next. For instance, researchers hope to observe planets like LHS 475b, a rocky world about 40 light-years away that is nearly identical in size to Earth. Early data suggest it may have a thin or non-existent atmosphere, but Webb's future observations could confirm whether it has carbon dioxide or other gases. If such a planet ever shows signs of water vapor or oxygen, it would be one of the most important discoveries in the history of science. Even more exciting are the prospects for detecting biosignatures, molecules that could indicate the presence of life. On Earth, gases like oxygen, ozone, methane, and nitrous oxide are produced in large amounts by living organisms. Finding such combinations on another planet would be a profound moment. Webb may not yet have the sensitivity to confirm such signals on Earth-sized worlds, but it is laying the foundation for future telescopes that will. Every spectrum it records helps scientists refine their models and techniques for interpreting the faint whispers of alien atmospheres. Imagine the Milky Way as a vast glowing island floating in an endless cosmic sea, a spiral of hundreds of billions of stars swirling together in quiet majesty. For centuries, humans looked up at the night sky and wondered where exactly we stood in this mysterious structure. The stars above seemed scattered and eternal, their light whispering stories that began long before the first humans ever walked the Earth. Yet, despite the beauty of this glittering dome above us, for most of human history, no one truly knew what the Milky Way was or where we fit within it. It was seen as a divine path, a river of light, or a trail of smoke from the gods' fires. But today, through the power of modern technology, Especially with the eyes of the James Webb Space Telescope, we are beginning to see our galactic neighbourhood with breathtaking clarity. And in doing so, we're realising just how small and fragile our local region truly is within the vast cosmic ocean that surrounds us. The Milky Way stretches for about 100,000 light-years across, a number that is nearly impossible for the human mind to fully imagine. If light, which moves faster than anything known in the universe, were to travel from one end of our galaxy to the other, it would take 100,000 years to complete the journey. Within this grand spiral lie hundreds of billions of stars, each possibly surrounded by planets, moons, and icy fragments, their own miniature systems of life and motion. Our Sun is just one of these countless stars, positioned about 27,000 light-years from the galactic centre, quietly circling around it every 230 million years. To Webb, this immense structure is not just a collection of stars, but a living system, full of movement, gas, dust, and mysteries that shape the very fabric of our existence. Before the launch of the James Webb Space Telescope in the early 21st century, astronomers had already made impressive progress in understanding the Milky Way. They used radio waves to trace cold hydrogen clouds, infrared telescopes to peer through thick dust, and optical telescopes to map nearby stars. Yet, even with all those tools, our view was still hazy, blurred by the dense clouds of gas that hide the galaxy's inner regions. The central bulge, where an enormous black hole named Sagittarius A resides, remained partly veiled, its details unreachable. But when Webb opened its golden mirrors to the sky, humanity gained a new window into this mysterious heart. Webb's infrared vision pierces through the dust like no telescope before it. Where ordinary light is blocked, infrared light passes through, revealing the structures hidden behind dark clouds. Through Webb's eyes, astronomers have begun to see clusters of stars forming in glowing cocoons of gas, streams of dust twisting into delicate filaments, and the faint traces of ancient stars that once illuminated the galaxy billions of years ago. It is as though Webb has lit a lantern in the fog showing the true map of our galactic home, not just its bright arms, but its silent corners and hidden depths. As Webb observes the Milky Way, it helps chart the positions and motions of countless stars. Each of these stars moves in its own orbit, like grains of sand drifting in an invisible current. Some belong to the thin disk of the galaxy, rotating in a neat spiral pattern. Others travel in the thick disk, where older stars move in more erratic paths. Still others form the halo, a vast faint sphere surrounding the galaxy, filled with ancient stars and ghostly clusters that may date back to the earliest days of the Milky Way's birth. By studying their light, Webb helps scientists calculate their distances, compositions, and ages, slowly building a three-dimensional map of our galactic neighbourhood. One of Webb's most astonishing contributions is its ability to peer into regions where stars are born, places that have always fascinated astronomers. These stellar nurseries are vast clouds of gas and dust that collapse under their own gravity to form new suns. In the Milky Way, such regions can be found in the Orion Nebula, the Carina Nebula, and countless smaller pockets scattered across the spiral arms. Earlier telescopes could see these nurseries only as bright patches of colour, but Webb reveals them in incredible detail. Pillars of gas sculpted by stellar winds, baby stars shining through their dusty cradles, and jets of material shooting into space like fireworks from newborn suns. These discoveries do more than just produce beautiful images. They also help us understand the structure of our galaxy and the story of our place within it. Every star Webb observes has a motion, a history, and a chemical fingerprint that tells where it was born. Some stars were formed near the galactic centre, where the density of matter is higher. Others were born in the outskirts, where gas is thinner and cooler. By tracing these differences, scientists can see how the Milky Way grew over billions of years, how it swallowed smaller galaxies, how its spiral arms formed and twisted, and how the stars in our local region came to be where they are today. Our solar system itself is only a tiny fragment within one of the Milky Way's spiral arms, known as the Orion Arm or the Orion Spur. This small section lies between two of the galaxy's major arms, Sagittarius and Perseus, and stretches for about 10,000 light-years. Within this modest region are stars like Betelgeuse, Rigel, and Sirius, each a brilliant beacon in the night sky. Yet when seen from a galactic perspective, these familiar stars are mere specks in a colossal ocean of light. Webb's observations remind us that what we once thought of as our neighbourhood is only a microscopic portion of a much greater cosmic structure. One of Webb's remarkable achievements is its ability to trace not only the structure of the Milky Way, but also its connection to other galaxies beyond. While we often imagine our galaxy as an isolated system, Webb reveals that it is only one of trillions scattered across the observable universe. Our Milky Way belongs to a small collection of about 50 galaxies called the Local Group. Among these, the most prominent members are the Andromeda Galaxy, a spiral system even larger than ours, and the Triangulum Galaxy. Around them orbit smaller, fainter galaxies, many of which are dwarf companions. Webb's powerful infrared eyes can see these faint systems better than ever before, helping astronomers understand how they interact, exchange gas, and shape each other's evolution. For example, the Milky Way and Andromeda are slowly moving toward one another, locked in a gravitational dance that will eventually lead to their merger about 4 billion years from now. Webb's detailed observations of star clusters and gas clouds in both galaxies allow scientists to simulate how that collision will unfold, how stars will swirl and mix, how new ones will form, and how the resulting galaxy will shine brighter and broader than either of its parents. Through Webb, we see not just where we are now, but also where we are heading in the grand story of cosmic time. Webb also allows scientists to explore the faint outer edges of the Milky Way, regions that were once invisible to telescopes on Earth. These outer zones, sometimes called the galactic halo, contain streams of stars that were stripped from smaller galaxies long ago. They are like fossils, silent witnesses of the Milky Way's violent youth, when it grew by swallowing smaller systems. Webb's sensitivity helps detect the dim glow of these ancient remnants, mapping their positions and motions across space. By studying their light, astronomers can reconstruct the family tree of our galaxy, tracing its growth from its earliest days to the magnificent spiral we see today. The telescope's role extends beyond the Milky Way itself. By observing other galaxies, Webb gives us context, a way to compare our home to the vast population of galactic systems scattered through the cosmos. Some are spiral galaxies like ours, with graceful arms spinning around bright cores. Others are elliptical, shaped like glowing eggs of stars. Some are irregular, distorted by collisions and gravitational tides. Webb can study their light across cosmic time, from the earliest galaxies born after the Big Bang to those thriving today. In doing so, it helps us understand where the Milky Way fits within the grand design of the universe. Looking at the Milky Way through Webb's eyes is like standing on the shore of a great ocean, realizing that what we once thought was the whole world is merely one beach among countless others. Each star is a wave, each nebula a shimmer of foam. The galaxy itself becomes a single island, floating in a boundless sea of galaxies that stretch as far as Webb's vision can reach. In this context, our Sun, and everything it warms, including Earth, becomes a grain of sand lost in the immensity of the cosmic shore. What makes Webb's mapping of our galactic neighbourhood so profound is not just the precision of its instruments, but the perspective it offers. For the first time, we are beginning to see the Milky Way not from within, as dwellers guessing at their surroundings, but almost as if from the outside, as explorers stepping back to see the shape of their own ship adrift in the cosmos. Webb's images reveal how our galaxy's spiral arms are rich with glowing hydrogen clouds, how star-forming regions cluster along these arms, and how dust lanes weave through them like rivers of shadow. They show the galactic bulge glowing with the light of billions of old stars and the faint halo stretching outward where the oldest remnants drift. Every discovery Webb makes adds another layer to this grand map. By measuring the light from distant stars and comparing their brightness, scientists can estimate how far away they are. By observing the motion of gas clouds, they can calculate how fast parts of the galaxy rotate. By detecting the faint signatures of certain elements, hydrogen, carbon, oxygen, and heavier metals, Webb helps determine the chemical evolution of the Milky Way, revealing how generations of stars have forged new matter from the ashes of the old. All of this mapping and measurement might sound purely scientific, but it carries a deep emotional resonance. When Webb shows us the vastness of our galactic home, it forces us to confront the smallness of our place within it. The distance between stars is so great that light takes years to cross even from one to the next. The nearest star to the Sun, Proxima Centauri, lies more than 4 light-years away, a journey that would take tens of thousands of human lifetimes with our current technology. And that is just within our own galaxy. Beyond that, the distances grow so enormous that they defy ordinary language. The gap between the Milky Way and Andromeda is about 2.5 million light-years. Beyond them lies an even greater cluster of galaxies, the Virgo cluster, tens of millions of light-years away. And further still, there are superclusters stretching across hundreds of millions of light-years, vast filaments of galaxies forming the skeleton of the universe itself. In this overwhelming immensity, the Milky Way is but one shining island. Webb's power lies in its ability to make that island real to us, not as an abstract concept but as a living dynamic world of stars, nebulae, and mysteries. Through its images, we can trace the swirling structure of the galaxy like veins in a leaf. We can follow the birth of stars and the death of others. We can glimpse the dusty cradle where our sun was born more than 4.5 billion years ago, and the ancient clusters that predate it by billions more. And yet, as Webb maps the galaxy, it also reminds us that we are travellers within it. The sun itself is not stationary. It drifts through space at about 220 kilometers per second, orbiting the galactic centre along with its planets, moons, and comets. Every second, our solar system moves thousands of kilometers through the cosmic void. It will take another 200 million years before we complete a single lap around the Milky Way's heart. By that time, the constellations we know today will have shifted beyond recognition. New stars will have appeared, and others will have vanished into darkness. The Webb telescope captures this motion in frozen glimpses of time. Each observation is like a still frame in a movie that has been playing for billions of years. When scientists combine these frames, the positions of stars, the shape of dust clouds, the drift of gas, they begin to see the larger motion of the galaxy itself, like the slow swirl of a hurricane seen from orbit. It is this sense of movement, this unfolding story of cosmic evolution, that gives meaning to Webb's maps of our galactic neighbourhood. Beyond even this, Webb's reach extends into the intergalactic medium, the thin, ghostly matter that fills the space between galaxies. This medium, though nearly empty, contains traces of the same elements that form the stars. By studying faint infrared signals, Webb detects the glow of hydrogen and heavier elements drifting between galaxies, showing how material flows from one cosmic region to another. This flow connects the Milky Way to the wider web of the universe, the cosmic filaments that link galaxy clusters together like threads in an immense tapestry. Through Webb, we can see that our galaxy is not isolated but part of a vast network, bound together by gravity and the silent exchange of matter and energy. Even within our local group, Webb helps uncover the smaller companions of the Milky Way, faint dwarf galaxies that orbit our own like satellites. Some of these are so dim that they escaped detection until recently. They contain only a few million stars compared to the hundreds of billions in the Milky Way, yet they are vital clues to how galaxies grow. Webb's sharp vision can pick out individual stars in these dwarfs, helping scientists measure their ages and metallicity, the abundance of elements heavier than hydrogen and helium. These details reveal whether the dwarfs are ancient remnants from the early universe or later fragments captured by our galaxy's gravity. The more Webb observes, the clearer it becomes that our galactic neighbourhood is full of unseen wonders. Between the spiral arms lie vast stretches of interstellar space, regions filled with cold hydrogen, drifting dust, and cosmic rays. These regions may seem empty, but Webb's infrared sensitivity detects faint glimmers of heat that reveal subtle patterns, wisps of gas shaped by stellar winds, glowing shells from long-dead stars, and distant clusters barely visible in ordinary light. Each new image deepens our sense of the Milky Way as a dynamic, breathing entity, not static, but alive with cycles of creation and destruction. In mapping the Milky Way, Webb is not only charting space but also time. Every beam of light it captures has travelled across vast distances, taking years, centuries, or even millennia to reach us. To look at a star 10,000 light-years away is to see it as it was 10,000 years ago. To see the galactic centre, 27,000 light-years distant, is to gaze into the deep past when humanity had not yet learned to build cities. Webb's map is therefore a time machine, allowing us to trace the evolution of our galaxy through the ages. All this knowledge transforms our sense of identity. Once, humanity believed itself to be the centre of everything, the Earth motionless, the heavens revolving around it. Then we learned that Earth was one planet orbiting an ordinary star. Then we discovered that our star was only one among billions in the Milky Way. Now, thanks to Webb, we can see that even the Milky Way is just one galaxy among trillions. Each step expands our vision and humbles our pride, showing that our local region, once thought immense, is in truth only a small drop in an infinite ocean. And yet, within that drop we find meaning. The same cosmic processes that Webb reveals, the formation of stars, the birth of planets, the forging of elements in stellar cores, are the very forces that created us. The atoms in our bodies were once part of ancient stars, scattered into space when those stars died. The dust that Webb sees drifting through the Milky Way is the same material from which new worlds and new lives may one day form. Thus, in mapping our galactic neighbourhood, Webb is also mapping the deeper story of existence, the endless cycle of creation, transformation and wonder that connects us to the cosmos. For thousands of years, humans thought the solar system was the central masterpiece of creation, the only true home for life and order in an otherwise cold and chaotic cosmos. Yet now, with the powerful golden mirror of Webb reflecting the faintest light from distant suns, that old belief fades into myth. What this telescope has revealed is that our solar system is only one among billions, a small member of a vast cosmic crowd. The universe, as seen through Webb's eye, is overflowing with star systems, each with their own planets, moons, and mysteries waiting to be uncovered. The telescope's observations show that nearly every star out there could have its own set of planets, forming miniature solar systems much like ours. Some are small and tightly packed, with planets circling close to their parent star in dizzying orbits. Others stretch wide, with worlds drifting in great arcs like Neptune and Uranus around our Sun. There are planetary systems made of fiery gas giants, others filled with rocky worlds, and still others that may carry frozen oceans beneath icy crusts. What was once thought to be rare has turned out to be common. The Sun, with its planets, is no longer special. It is simply one of many in the crowded neighbourhoods of the Milky Way. This discovery did not happen overnight. For centuries, people could only guess what might exist beyond the faint points of light scattered across the sky. Even with the invention of telescopes, stars remained just that, bright dots, impossible to study in detail. The idea of planets orbiting those distant stars seemed like speculation. It was not until the late 20th century that astronomers began to detect the first confirmed planets outside our solar system. The first discoveries were thrilling but few. By the early years of the 21st century, the number of known exoplanets had risen to hundreds. Yet Webb's arrival changed everything once again. With its immense sensitivity to infrared light, a form of light invisible to human eyes but rich with cosmic information, Webb began to uncover planets that older telescopes could never have found. What the telescope revealed was astonishing. The galaxy is bursting with solar systems. Some estimates now suggest there could be as many as 100 billion planets in our Milky Way alone. That means, on average, there might be more planets than stars. Each glimmer in the sky could have its own set of worlds circling around it, worlds with their own seasons, climates, and perhaps, in some cases, life. The scale of this realization is staggering. Humanity once saw the solar system as a precious island in an infinite sea, but Webb has shown that it is just one pebble on an endless beach. When Webb peers into distant star-forming regions, such as the Carina Nebula or the Orion Complex, it captures breathtaking images of stars being born. In those swirling clouds of gas and dust, the telescope's instruments detect disks of material encircling young stars. These disks, known as protoplanetary disks, are the nurseries of planets. They glow faintly in the infrared, revealing warm dust and gas slowly coming together under gravity's pull. Over millions of years, the particles in these disks clump together, forming rocks, then planetesimals, and finally full-size planets. By studying these regions, Webb allows astronomers to watch the process that once shaped our own solar system nearly 5 billion years ago. It is like watching history repeat itself across the universe. Each new observation adds to the growing realization that the process of planet formation is not an exception, it is the rule. Wherever stars are born, planets soon follow. Webb's instruments can even analyze the chemical fingerprints in the light from these disks, showing the presence of carbon-based molecules, water vapor, and silicates. These are the very ingredients that made Earth what it is. When astronomers see these same elements and compounds swirling around distant stars, it suggests that the basic recipe for life's building blocks is spread far and wide across the cosmos. In many cases, Webb has even been able to study the atmospheres of exoplanets directly, a task that was once thought impossible. By watching as a planet passes in front of its star, Webb captures the faint starlight that filters through the planet's atmosphere. That light carries telltale signs of the gases within: water vapor, methane, carbon dioxide, and even more complex compounds. Through such measurements, astronomers can begin to tell what kind of world they are looking at. Is it hot and stormy, like Jupiter? Cloudy and humid, like Venus? Or perhaps cool and potentially habitable, like Earth? Each discovery adds another piece to the growing mosaic of worlds beyond our own. One of the most remarkable things about Webb's discoveries is how diverse these star systems are. Some defy every expectation formed from studying our solar system. There are planets that orbit their stars in just a few hours, so close that their surfaces melt into vapor. There are others that drift so far from their stars that they receive almost no light or warmth, becoming dark, frozen spheres wandering in the cold. There are worlds made mostly of water, others of iron, and still others that are so puffy and light that they would float in water if such a thing were possible. Some systems have 2 or even 3 suns, where days and nights are painted in shifting hues of gold and red. In some cases, giant planets orbit close in while small rocky ones circle far away, the reverse of our own arrangement. The universe, it seems, is endlessly creative. What Webb has done is to take all these scattered discoveries and place them in context. With its ability to see both faint and distant light, the telescope can study not only the planets themselves, but also the environments that give rise to them. It peers into the dusty cradles of young stars, revealing how gravity, radiation, and chemistry combine to sculpt the birthplaces of planets. It observes ancient galaxies, showing that planet formation likely began not long after the universe itself took shape. This suggests that worlds have been forming for more than 13 billion years, nearly the entire lifetime of the cosmos. There may be planets out there that are far older than Earth, orbiting stars that have long since faded away. The abundance of star systems also changes how astronomers think about life beyond Earth. If there are billions of solar systems, each with multiple planets, then the odds of some of them hosting life, even simple microbial life, become far higher. For much of history, people wondered if Earth was the only living world. Now, that question seems less likely than ever. Webb has not yet found direct evidence of life, but it has found the environments where life could exist. Planets with water, with stable temperatures, and with atmospheres that could protect life from harmful radiation. It is only a matter of time before telescopes like Webb or its future successors identify clear signs that living processes are taking place elsewhere. Even among the first systems studied by Webb, astronomers have found worlds that stir the imagination. There are exoplanets roughly the same size as Earth, orbiting stars smaller and cooler than the Sun, known as red dwarfs. Some of these stars are so close that their planets could be studied in extraordinary detail. One such system, TRAPPIST-1, contains 7 Earth-sized planets, 3 of which lie in the habitable zone, where temperatures might allow liquid water to exist. Webb's observations of this system have already begun to reveal information about their atmospheres and compositions. Though it is still uncertain whether these worlds are truly habitable, they remind humanity that planetary systems like ours are not isolated miracles, but recurring patterns written into the fabric of the cosmos. The telescope's data also show that planets form around stars of all kinds, not just those like our Sun. Massive blue stars, small red dwarfs, and even faint brown dwarfs can host planets. This variety suggests that the conditions for forming planets are extremely flexible, occurring in nearly every environment where stars exist. Some planets even form in the aftermath of stellar explosions, orbiting pulsars, the dense remnants of dead stars. The resilience of planetary formation is one of the universe's most astonishing features. Even in the most violent and unlikely places, gravity finds a way to create order. As Webb continues to explore, it is also rewriting our understanding of the solar system itself. By comparing the distant systems it observes with our own, astronomers gain new insight into how Earth and its neighbours came to be. They can now place our Sun's planets within a much broader cosmic pattern, understanding which features are common and which are rare. For instance, our solar system's wide spacing and relatively stable orbits may be unusual compared to the tight, chaotic systems seen elsewhere. The lack of a super-Earth, a planet larger than Earth but smaller than Neptune, common in many other systems, makes our arrangement distinctive. Yet, despite these differences, the same fundamental processes that built distant planets also shaped our own world. In this way, Webb has made the universe feel both vast and familiar. Each distant solar system it observes is a reflection of our own cosmic story, a reminder that the forces shaping those faraway worlds are the same ones that sculpted Earth from dust and fire billions of years ago. Light from those systems has travelled for centuries, millennia, or even billions of years before reaching Webb's mirror, carrying messages from the past. By studying them, humanity looks not just outward but backward in time, tracing its own origins across the eons. There is also a quiet, humbling truth in Webb's revelations. If our solar system is one of billions, then the sense of cosmic centrality that once comforted humanity must give way to a new kind of wonder, one rooted in connection rather than uniqueness. The universe is not organized around us. We are part of it, woven into the same vast tapestry as every other star and planet. The sun is merely one among countless others, burning across the dark, each surrounded by its own family of the worlds. This understanding does not diminish our place, it enriches it. To know that there are countless other solar systems is to know that creation is far grander and more generous than we once imagined. When Webb captures light from distant planetary systems, it is not only recording data, it is witnessing the ongoing act of creation across space and time. It sees the delicate balance of dust and radiation, the forming of atmospheres, the slow dance of gravity shaping worlds. In the faint glow of those young stars, astronomers can trace the same sequence of events that long ago gave rise to Earth, oceans, and life itself. Each image is a kind of mirror, reflecting both the universe's diversity and its unity. The telescope's instruments, such as its near-infrared spectrograph and mid-infrared imager, can separate light into precise spectra, allowing scientists to detect tiny differences in colour that reveal what materials are present. In doing so, Webb acts like a cosmic detective, uncovering clues hidden in the light from alien worlds. It can detect the heat given off by planets too faint to see directly, revealing their size and temperature. It can even capture the glow of distant dust belts that may one day form new planets, much as our own solar system's asteroid and Kuiper belts mark remnants of its formation. Each new observation adds to the realization that the universe is filled with endless variation and possibility. Some planets circle binary stars in elegant figure-8 orbits. Others move in eccentric paths that bring them dangerously close to their suns before flinging them out again. There are rogue planets, worlds that have been ejected from their home systems entirely and now drift alone through interstellar space. Webb's sensitivity might even allow astronomers to detect the faint heat from some of these lonely wanderers, showing that even the emptiest regions of the galaxy are not truly empty. Beyond our Milky Way, Webb's reach extends to other galaxies, where it can detect the faint glow of stellar nurseries and planetary disks. This suggests that solar systems have been forming not just here, but everywhere, for as long as galaxies have existed. The process of creating stars and planets appears to be a universal pattern, one that repeats itself across cosmic history. In distant galaxies billions of light years away, light that left when the universe was young reveals stars surrounded by swirling material, showing that even then new solar systems were taking shape. This discovery means that planets may have existed almost from the beginning, providing stable environments for life to emerge long before Earth was formed. The universe is a place of extraordinary vastness, a scale so immense that it is almost impossible for the human mind to fully grasp. When we talk about distances in our everyday lives, we often use units like meters, kilometers, or miles, and even the largest cities, countries, and oceans seem comprehensible in those terms. But when it comes to the cosmos, these units are simply too small to be useful. The distances involved are so enormous that scientists use light as a measuring tool. A light year, which is the distance light travels in a single year, is approximately 9,570,720,000,000 kilometers. Light, traveling at nearly 300,000 kilometers per second, can cover unimaginable distances in a very short amount of time compared to the scale of the universe. Yet even a single light year is just a tiny fraction of the distances between galaxies and the edges of the observable universe. Starting closer to home, within our own solar system, distances can be measured in terms of light hours or light minutes. For instance, the average distance from the Earth to the Sun is about 8 light minutes, meaning that sunlight takes around 8 minutes to travel across the vast emptiness of space before it warms our planet and allows life to exist. This simple fact is astonishing when we think about it. When we look at the Sun in the sky, we're seeing it not as it is at this very moment, but as it was 8 minutes ago. The light has travelled all the way from the Sun across approximately 150 million kilometres of space, finally reaching our eyes. And if we look at planets farther out in the solar system, these distances stretch even more. Jupiter, the largest planet in our solar system, is about 42 light minutes from the Sun, while Neptune, the farthest of the classical planets, sits about 4 light hours away from our central star. These measures, though enormous compared to human scales, are still small when compared to the distances between stars in our galaxy. Once we step beyond the solar system, the scale grows dramatically. The nearest star to the Sun is Proxima Centauri, which lies about 4.2 light-years away. That means the light we see from Proxima Centauri today actually left that star more than 4 years ago. It is difficult to imagine travelling such a distance in a human lifetime. Even the fastest spacecraft humanity has ever built, such as the Voyager probes launched in the 1970s, would take tens of thousands of years to reach even the closest stars. And yet, even at this distance, Proxima Centauri is merely a neighbour, one tiny point in the vast Milky Way galaxy, which contains hundreds of billions of stars, each potentially with its own planets, moons, and complex systems. The Milky Way itself is about 100,000 light-years across, which means that light travelling at the incredible speed of nearly 300,000 kilometres per second would still take 100,000 years to move from one edge of the galaxy to the other. To put this into perspective, 100,000 years is roughly 5 times the span of human civilization, from the beginnings of settled agriculture to the present day. Within this immense galactic scale, the distances between stars are still mind-boggling. Most stars in the Milky Way are separated by several light-years, sometimes tens of light-years, from their nearest neighbours. Even though these stars may seem close when viewed on a night sky, the reality is that each star exists in its own vast emptiness. Between them lies mostly nothing, a near-perfect vacuum that stretches over vast distances. Astronomers often use the term parsec to express these distances more conveniently, with 1 parsec equal to approximately 3.26 light-years. So, for example, a star located 10 parsecs away is about 32 light-years distant. These units, light-years and parsecs, help scientists and astronomers make sense of the staggering expanses of space, which otherwise become incomprehensible when expressed in kilometres or miles. The scale of the universe only grows as we move beyond the Milky Way. The next galaxies, which can be seen with powerful telescopes, are measured in millions of light-years. The nearest large galaxy to our own is the Andromeda Galaxy, which lies approximately 2,500,000 light-years away. Andromeda is a spiral galaxy, somewhat similar to the Milky Way, containing perhaps 1 trillion stars. When astronomers observe Andromeda, they are looking back in time by over 2 million years. The light we see today left that galaxy long before humans existed as a recognizable species, long before our ancestors invented tools, language, or fire. Looking even further, we encounter galaxy clusters, which are massive gatherings of hundreds or even thousands of galaxies bound together by gravity. These clusters can be hundreds of millions of light-years across, forming cosmic structures so large that they stretch our understanding of space. Beyond clusters, the scale becomes truly astronomical, measured in billions of light-years. The observable universe, which is the portion of the cosmos that we can see and measure from Earth, spans an incredible distance of about 93 billion light-years in diameter. This immense expanse contains more than 2 trillion galaxies, each with billions or even trillions of stars. It is difficult to comprehend such numbers. The galaxies are not scattered randomly, but often arranged in filaments and walls, separated by enormous voids that are almost entirely empty. These structures form a kind of cosmic web, with galaxies threading across space in long chains, creating an intricate and magnificent architecture. When we observe the universe at such great distances, we're also looking back in time. Light that has travelled for billions of years allows astronomers to see galaxies as they were in the distant past, not as they are now. For example, some of the earliest galaxies detected by powerful observatories like the James Webb Space Telescope formed just a few 100 million years after the Big Bang, approximately 13.8 billion years ago. Observing these galaxies is like peering into a cosmic time machine, revealing the infancy of the universe and the beginnings of galactic formation. The photons reaching our instruments today have journeyed through nearly the entire history of the cosmos, travelling across space that has expanded tremendously over time. The concept of distance in the universe is further complicated by the expansion of space itself. When astronomers say a galaxy is 10 billion light-years away, they mean the light we see left that galaxy 10 billion years ago. During that time, the universe has continued to expand, and the galaxy has moved much farther away than it was when the light first departed. This expansion means that distances in the universe are not static but constantly changing over cosmic timescales. To describe such distances more accurately, scientists use terms like a moving distance, which accounts for the stretching of space, allowing them to better understand the true separations between galaxies. Even within a single galaxy, the scale can be immense. The Milky Way, with its spiral arms extending across 100,000 light-years, contains regions of extreme density as well as vast stretches of almost complete emptiness. The solar system resides in a relatively quiet neighbourhood, about 27,000 light-years from the galactic centre, nestled in one of the spiral arms called the Orion Arm. Here, stars are spaced far enough apart that direct collisions are exceedingly rare, yet close enough that gravitational interactions shape the motions of stars and star clusters over millions of years. Observing these motions allows astronomers to infer the distribution of mass within the galaxy, including the mysterious dark matter that cannot be seen directly but exerts a gravitational influence on visible matter. Beyond the Milky Way, the diversity of cosmic distances becomes even more apparent. Galaxies in the local group, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, are separated by distances ranging from a few 100,000 light-years to over 2 million light-years. In contrast, the Virgo cluster, which is the nearest massive galaxy cluster to our local group, is about 55 million light-years away. This range illustrates the difference between local and large-scale structures, showing how the universe is hierarchically organized into stars, star systems, galaxies, groups, clusters, superclusters, and vast filaments. The scale of cosmic distances also has profound implications for the study of light and radiation. Light from distant objects travels through the intergalactic medium, which is not entirely empty, but contains thin gas and dust that can absorb or scatter certain wavelengths. As light travels billions of light-years, it becomes redshifted, meaning its wavelength stretches due to the expansion of the universe. The farther an object is, the more its light shifts toward longer wavelengths. For example, ultraviolet light emitted by young stars in distant galaxies can be observed as infrared light by telescopes like the James Webb Space Telescope. Understanding these effects allows scientists to reconstruct the properties of galaxies, their star formation rates, chemical composition, and the processes that governed the early universe. Even measuring the scale of the observable universe is a formidable challenge. When astronomers say that the universe is approximately 93 billion light-years across, they are referring to the diameter of the region from which light has had time to reach us since the Big Bang. Beyond this horizon lies more universe that we cannot yet see, potentially infinite in extent. The observable universe is a sphere centered on Earth, defined by the distance light has traveled in the 13.8 billion years since the universe began. Within this sphere, galaxies are not only at vast distances but also in motion, influenced by gravity, dark energy, and the initial conditions set by the Big Bang. Even the concept of a light-year can be challenging to fully appreciate because it is tied to both space and time. A single light-year represents not just a measure of distance, but also a measure of the time it takes for information, in the form of light, to travel across that distance. This dual nature of light-years allows astronomers to observe the universe as it once was, turning every observation into a glimpse into the cosmic past. When we observe a galaxy 1 billion light-years away, we see it as it appeared 1 billion years ago, long before the Earth had its current continents, oceans, and life forms. This interplay between distance and time is fundamental to understanding the universe and allows astronomers to construct the history of cosmic evolution. The vastness of cosmic distances also highlights the limits of human exploration. Even if humanity were able to travel at the speed of light, which is physically impossible according to our current understanding of physics, journeys to even the nearest stars would take years, while reaching distant galaxies would take billions of years. This limitation underscores the unique role of telescopes and observatories, which act as our eyes across space and time, enabling us to explore regions that are far beyond the reach of spacecraft. Instruments like the Hubble Space Telescope and the James Webb Space Telescope collect photons that have travelled for billions of years, allowing scientists to study the origins, evolution, and structure of the universe. From the scale of our solar system to the Milky Way, and then to the observable universe, the progression of cosmic distances is staggering. Distances grow from light minutes between planets, to light years between stars, to millions and billions of light years between galaxies and clusters, and finally to tens of billions of light years across the entire observable universe. Each step in this progression demonstrates a new level of vastness and complexity, revealing the universe as an interconnected network of stars, galaxies, and cosmic structures stretching across incomprehensible distances. Throughout human history, understanding these distances has been a gradual process. Early astronomers could only see the Milky Way as a faint band across the night sky, unaware that it was just one galaxy among countless others. The invention of the telescope in the early 17th century allowed astronomers like Galileo to resolve stars more clearly, but it was not until the 20th century that the true scale of the universe became apparent. Edwin Hubble, in the 1920s, demonstrated that galaxies were receding from one another, revealing the expanding universe and establishing that the Milky Way was merely one galaxy in a vast cosmic ocean. Since then, advances in technology, from radio telescopes to space-based observatories, have extended our vision to billions of light years, allowing us to map the structure of the universe in unprecedented detail. The comprehension of cosmic distances also influences other areas of science. In astrophysics, knowing the distances to stars and galaxies allows scientists to calculate their intrinsic brightness, mass, size, and composition. In cosmology, the distribution of galaxies across billions of light years informs theories about the formation of the universe, the role of dark matter, and the effects of dark energy. Even in the search for life beyond Earth, understanding distances helps identify exoplanets within habitable zones, where liquid water and the conditions for life as we know it might exist. Distances in the universe can also inspire awe and reflection. The fact that light from distant galaxies has travelled billions of years to reach us emphasises the temporal and spatial vastness of the cosmos. Every photon captured by a telescope carries a story from the distant past, a message that has traversed the expanse of space to tell us about the formation of stars, the assembly of galaxies, and the processes that govern cosmic evolution. The mind struggles to reconcile these immense distances with our everyday experiences, yet the universe continually invites us to expand our understanding, to imagine scales that dwarf human existence, and to appreciate the intricate and magnificent architecture of the cosmos. Even as scientists continue to refine their measurements, the challenge of making sense of such scales persists. Techniques like parallax, standard candles, redshift analysis, and gravitational lensing allow astronomers to estimate distances with remarkable accuracy, but they also reveal just how complex and dynamic the universe is. Light years, millions of light years, and billions of light years are not just numbers, they are gateways to understanding the history, structure, and destiny of the cosmos. They remind us that the universe is not static, but ever-changing, with galaxies forming, evolving, colliding, and merging over billions of years. The journey from the scales of light hours within our solar system to the billions of light years across the observable universe is a journey through space and time itself. Distances that are almost unimaginable reveal the grandeur and complexity of the cosmos, and the tools we use to measure them allow us to peer back into the history of everything that exists. From the nearest planets to the farthest galaxies, from light that travels in minutes to light that travels for billions of years, the universe presents a panorama of unimaginable scale. Every observation, every measurement, and every calculation helps humans make sense of our place in this vast expanse, showing that while we occupy an infinitesimal speck of space, our understanding can stretch across the cosmos itself, bridging the gap from the familiar to the incomprehensible.